Hello everyone, welcome for today's quantum spacetime seminar. Today we are very happy to have Sandipan Kundu from Johns Hopkins University, and he's going to tell us about Swampland conditions from CFT. Over to you, Sandipan.
Thank you very much for the invitation. Thanks for the introduction. I'm actually very happy to be back at TIFR, even though virtually. Yeah, hopefully I could be there at some point in person.
Yeah, we would love to.
So this talk is based on a recent paper of mine, probably from like 3-4 months back. Before I proceed, please feel free to stop me whenever something is not clear or whenever you have any question. Otherwise, it kind of feels like I'm just talking to my computer.
Hey, Sandipan, I'm sorry, maybe this is only me, but I'm hearing you a little softly. So if it's possible for you to come nearer your mic or something. Then.
Oh, actually, okay, that's good. Let me try to, actually, this might be a problem of Zoom as well. Let's see. Is this better?
For me, it's much better.
Okay. So as I said, I'm going to talk about this paper of mine from a couple of months back. So the main idea is actually very simple. The goal is to constrain the space of effective field theories from general principles and symmetries. In last 10 years or so, this idea has gained a lot of attention, mainly because of the success of the conformal bootstrap program. But this is not a new idea by any means. This general idea has been around for ages, probably as long as quantum field theory itself. So one of my favorite example of this general idea, for some reason it didn't change. Okay. So one of my favorite example of this general idea is this bound on the scalar effective field theory with higher derivative interaction. So let's take a scalar effective field theory, which is massless and has shift symmetry, and we add this interaction. So this interaction is non-renormalizable. So that means this is basically an effective field theory which is valid up to some cutoff scale. So for this set of authors, Adams, Ahmed, Dvorsky, Nicolis, and Ratazzi, they showed that this coupling constant mu, it has to be non-negative. So otherwise, this effective field theory can never be UV completed. Or said in a different way, if you start from any UV complete theory and then you integrate over some massive states, you integrate out some massive states, and you recover this effective field theory at in the IR, you will never be able to generate an effective field theory with negative mu. So so this is actually a remark, at least to me, this is a remarkable result, because this conceptually, this is completely different from our traditional understanding of Wilsonian EFT, where everything goes. And this bound is basically saying, no, that's not true. There are effective field theories which look completely all right, but they are actually problematic. And more practically, this bound played a very important role in the proof of the 4D theorem by Kumar-Gursky and Schwimmer. But this is not just an accidental bound. This bound is actually part of a more general idea. That's the idea of Swampland due to Vafa. So the statement is only a subset of all effective field theories can actually be UV completed. And there are effective field theories that are in the Swampland, which can never be UV completed. So this is the general idea, and actually obviously this idea was originated from string theory, but there are many compelling evidence in favor of this idea directly from quantum field theory. So there is a growing body of literature with similar precise bound on IR couplings from UV consistency. Just to give you some idea, so these are some of the recent bounds on this on IR effective field theories from some UV consistency. This is not a complete list of all the references. I'm sure I'm missing some more recent references, but the important point is there are many such bounds. And another interesting thing is that most of these bounds, in fact, almost all of these bounds, they are rather recent. So they are after, like from 2017 or after that. That's because a lot of new tools have been developed in last couple of years. So all this kind of tools or arguments or basically any kind of theorem that you can derive on the low energy effective field theory, they have a couple of things in common. First important thing is these bounds, they are independent of the details of the UV complete theory. So that's a very good thing. You don't actually have to know the exact form of the UV complete theory. But that does not mean you don't have to assume something about the full theory. So in all these references that I showed you, all of them, they basically have to assume something about the amplitude in the full UV complete theory. So for example, I think most of this, I think other than one, all of these examples, they deal with 2-to-2 scattering amplitude. So what we have to assume to derive any bound is basically the 2-to-2 scattering amplitude is analytic. So when I say analytic, basically I mean in the complex S-plane, it's analytic everywhere other than on the real axis. It obeys the standard partial wave unitarity. It's crossing symmetric, and we have to assume something about Regge boundedness. So the Regge boundedness statement is the forward limit of the amplitude for large S, it's bounded by S squared. It's a strict bound. So under these assumptions, all the bounds, all the references that I showed you, all the bounds are derived under the assumption that the 4-point scattering amplitude obeys these conditions even in the UV.
So Sandipan, do you know where this fourth condition comes from?
You mean like what's the reason?
Yeah.
The first easy answer is like in the Adams et al. Paper, if you just go step by step, so you see that the only way you can, so all these bounds, they are basically in the left hand side you have some IR quantity, in the right hand side you have some expression of the UV amplitude which you cannot compute, but like you can argue from unitarity or something else that quantity is positive or something like that. So you need analyticity just to relate UV and IR. And then you need unitarity to prove something which is like you have to prove that the right hand side is positive, for which you need unitarity. Yeah. Crossing is basically, let's see how I can.
Sorry, no, I was just talking about the fourth condition.
Oh, only the fourth one? Well, like, why do you need it, or like, what's the justification?
What's the justification for it?
Okay, I'm going to talk about that. Okay. That's one of the main reasons that's one of the motivation behind the work I'm discussing.
I see. And you must go on, and everybody else on this call knows this better than me, but Sandipan, is a kind of bound on the growth in S square coming because you want to complete some contour going along some big arc and you want the amplitude to die fast enough?
Yeah, exactly. Exactly.
Okay.
Yeah. So you are basically dropping the contour at infinity, and this is the condition that's required for that. So mathematical test.
Okay, that's tied to 4, is it? That one is tied to number 4, Regge boundedness,
Yes,
or no?
yeah, that's right. That's right. Yeah, that's right. That's right. That's right. That's right.
Thank you. Please go ahead.
Yeah. So these assumptions, they are well motivated, but still these assumptions have not yet been rigorously established. In fact, the situation is worse for massless external states, where like for massive states, there are some very general statements that you can make, but when you have massless external states, actually many of these assumptions are just assumptions. They are not very rigorous. So that's kind of unsatisfying. Let me just talk about, since like we were discussing Regge boundedness anyway, let me talk about Regge boundedness for a couple of minutes. So Regge boundedness actually follows from Prasad bound. It's actually a way weaker condition than the Prasad bound. But it's also known that Prasad bound is not applicable when you have massless states in the theory. So for the Prasad bound, you need a mass gap. So in general, especially when there are massless states in the theory, Regge boundedness condition is, you cannot actually motivate Regge boundedness condition that well. And that's
even when the external particles are massive.
Yes, that's right. That's right. And this is very unsatisfying, at least to me. That's because like some of the effective field theories that we like to study are basically effective field theories of massless Gaussian modes. And in those kind of theories, obviously, like these assumptions are not that rigorous. And that's kind of a very unsatisfying nature of this kind of arguments.
And sorry, what was capital D there? The number of space-time dimensions?
That's space-time dimension. That's right. That's space-time dimension. Yes.
Thank you.
Sorry, Sandipan.
Yes.
Suppose we look at the theories where infrared divergences are not a problem. So let's say gravity in high enough dimensions. Is there an expectation for what replaces, even if there's no proof, is there an expectation for what replaces S log S for massless theories? Clearly, it can't be S log S because there's no scale.
Exactly.
There's nothing to make the scale. Yeah. So the naive guess might be that you just don't have the log S, that it's just S. Could that be, is that an expectation that people have, or?
Definitely, like this S square bound, it's something like my impression is this is something people believe in the sense like this is not like they think this is a true statement. And it's also like if you ask people who are working on a conformal bootstrap, they will probably tell you the linear S bound is probably true, because like this is the linear S bound is very close to like the chaos bound, like the chaos growth bound in some sense. Not chaos growth bound actually. So this Regge bound is kind of similar to some Regge bounds in CFT correlators, and there it's not just that it has to be less than S. CFT Regge correlators, they are always bounded, like they cannot diverge at all. So if you like just take that literally and convert that into a statement about scattering amplitude, it will translate into the statement that S is growing slower than S.
Right. But, so is that an expectation you have? That, I mean, if, for instance, that in a theory with gravity, the bound will be S? Or with any massless particles? Or is that, you don't want to, yeah.
I had that impression like before doing this work, and I kind of have some other, like I'm not confident right now, because I'll tell you, like there are.
Thank you. Sorry for interrupting.
That's part of
Okay.
You must go on, but may I ask Shiraz and you, Sandipan, a remedial question, which is, Shiraz, for a theory of gravity, why couldn't the scale in the log be the mass, be m Planck?
Yeah, I suppose it could, except that in the Froissart bound, what appears in that scale is S divided by the mass of the particle. Oh, the mass gap of the theory, more like.
Oh.
So, that sort of, if you look from continuity there.
I see. Okay, thank you. Thank you.
And the situation is actually a lot worse when you include dynamical gravity. The reason is, so in all this, most of these arguments, you consider the forward limit of the scattering amplitude. And if you take the even the simplest diagram, which is basically a single graviton exchange, in the forward limit it has a pole. So that all these arguments, they are kind of like, they don't work when you have that p-channel pole. So that's a technically, like, having dynamical gravity is actually, it's very challenging. That's a conceptual, really an important conceptual problem, because in the Swampland picture, it's basically a picture about quantum gravity. So like whatever we are doing, it's important that we can incorporate dynamical gravity in that picture. But this issue has been solved recently by Karen Watt, Mazak, Rastelli, and Simmons-Duffin. So what they did is basically they did a very similar kind of, they made a very similar kind of argument, but they did not study scattering amplitude in the forward limit. They studied scattering amplitude at finite but small impact parameter. And if you do that, actually, like this t-channel pole, obviously, like it's not, you're studying it in the impact parameter space. So like this, all the problems with t-channel poles, that's not in their argument. But conceptually, one problem is still there. It's basically, when you have dynamical gravity, validity of the Reggie boundedness condition is even more unclear. The reason is, even this simple diagram where you're exchanging a single graviton, that grows as a square. And you like the requirement is it's always growing slower than a square. So just the simplest diagram seems to contradict that that statement.
Sandipan, if you iconolize gravity and you look at it in the large S fixed T limit, then how does it go? Presumably at large S fixed T, this iconalization is governed by distance where classical gravity holds. And in that, what is the answer there? Do you know?
I don't remember now, but like that's a known answer, but I don't remember right now.
But do you know if it's less than S square?
Generally, if you iconolize it, so basically you're talking about going to the impact parameter space and then doing the iconization, right?
Yes. So go to large impact. I presume that that large impact parameter dominates this process.
So I think if you if that it goes as, I think, S times exponential of S log B, something like that.
Oh, exponential of S log B.
With a minus, like the sign, I think is minus. Yeah. I'm trying to remember the expression for the phase shift.
Yeah.
So obviously that's the thing that's going to be exponentiated.
Yeah. Yeah.
So no, I think it's exponential now. It's exponential S log B. Yeah, I think that's in 4D, that's the answer.
Exponential of S log B. So what will that translate to for how A grows as function of S at fixed T? I'm sorry to ask, but just if you happen to know.
In 4D, I think it should be, generally there is a log of the impact parameter.
Log of the impact parameter, no S, and then there will be an extra S in the kinematics and going from.
Yeah, I don't remember.
Fine. Thank you. Sorry to disrupt.
Yeah, phase shift. I think the phase shift goes as, I think, S square log B. So that's I think kind of the right answer, but then when we exponentiate, probably like that, there might be some extra factor of S that I don't remember right now.
Yeah, the more general point was that in gravity, if it's true that large S fixed T happens at large impact parameter, we shouldn't have to guess whether or not this bound applies. We could just calculate it.
Yeah.
It's just a classical calculation.
That's right.
Okay.
That statement is probably known, but I think like the people who complain, the complaint is like, then like you have to have like include the other higher spin states, and like we don't know how they'll behave. Hopefully like they will also like behave something like string theory and making it softer and softer, but like those are extra assumption.
Yeah. But I thought the worry was about the exchange of the graviton.
The worry is about like the single graviton exchange. That was one of the worry. Yes,
but that might just be cured by iconization. Right?
I agree. Yeah, that might not be that bad of problem. Yes.
Okay. Thank you.
The main point that I want to emphasize in this talk is basically all these loopholes that are there in this asymmetric space argument. They can be avoided by studying effective field theories in ADS. The reason is, so when we study this effective field, any of this kind of effective field theories in ADS, there is a dual CFT description, and then in the dual CFT description, we don't actually have to assume any of this kind of like Reggie boundedness or this kind of condition. We can just start with all the known, all the well-established CFT axioms, and then from there we can actually try to study the effective field theory in ADS. So morally speaking, this is basically this setup is basically the setup of like a quantum field in a box, where ADS spacetime plays the role of the box, and the expectation is so like whatever bound we get from some kind of high energy argument, so that should not depend on where that box is if the size of the box is very large. So that's the main idea that I'm going to explore today.
Sorry, Sandipan. Of course, you'll have a lot to say, but just to ask, is it then in the long term, as part of this program, perhaps possible to turn it around and say, do the principles of the conformal bootstrap lead to a kind of proof of whatever it is, Froissart bound, Regge boundedness, or any of the other assumptions? Sorry.
That would be a really nice goal for this program. Yes.
Okay. Thank you.
So, because we have learned a lot about CFT bounds from conformal bootstrap, so what we can do, we can just use all these tools in conformal bootstrap and use them to constrain the space of effective field theories in ADS. So that's something we can do really well in this ADS language. Another advantage of this setup is that in this setup, inclusion of gravity is trivial. So that is like if I try to include gravity, it's just basically computing an additional Witten diagram. That's it. There is no conceptual complication.
So the hope would be.
Sorry, Abhishek, go on.
Sorry, the hope would be to finally extract some information about bounds in flat space, right?
Yes, that's right.
And there be some subtleties from going from ADS to flat space also?
Generally, that's a very good question. So there are two things. First of all, like just studying effective field theories in ADS and finding bound, that's already like that. That's already in itself, that's a well-defined. Then if I want to go to take the flat space limit, most of the time, that limit is kind of, that limit is actually like very well-defined. Actually, like when we study non-generalizable theories, like the effective field theories that the kind of effective field theories that we are studying, they are actually, the flat space limit is very, like that's, like there is no problem whatsoever. You can just take the flat space limit. But when you have like renormalizable coupling, they are actually more problematic. So then you have to be very careful when you take the flat space limit. So generally, the statement is there is always like it's obviously it's not a theorem that I can prove that you can always take the flat space limit, but there is always a limit which is basically in which you recover the flat space bounds. So generally the problem is not the taking the large R radius limit for the effective field theory. It's basically sometimes in the dual CFT, when you take large R radius limit, like some of the anomalous dimensions, they become too big. Mm-hmm. So even though in the effective field theory language, there is nothing funny going on, but in the dual CFT, there can be things that are not that well defined. Mm. We have to avoid those kind of situations.
No, but one funny thing that may go on in the bulk is that the interactions don't necessarily happen in a small patch, because that is what will give you the flat space limit, right? The interaction could simply occur everywhere in the ADS, and then you may not be able to take the flat space limit. Yes. That is also a worry, isn't it?
Yeah, that's very possible. So that's why, like, we have to be very careful what kind of observables we're studying in the CFT to derive bounds. So one easy answer is always try to study things like CFT Regi correlators, because they are basically like high energy scattering inside ADS. Those kind of like that you can derive from there should probably like there. If you take the flat space limit, they should be well behaved.
Okay.
But if you take, there are other correlators you can compute that which can be sensitive to like how you take the larger radius limit, things like that.
Yeah. Thanks.
Any other question?
Yeah, Sandipan, sorry. You said inclusion of gravity is trivial. I was wondering whether it was necessary. I mean, will you require your CFT to have a stress tensor, or will everything go through without that?
Both, in the sense that if I just want to study effective field theory in ADS, I can always take the limit that the number, like basically like the central charge is so large, the stress tensor is decouples completely from the low energy spectrum. Then they are basically whatever bound I derive in that setup, it's basically they are the bounds on just the effective field theory without any dynamical gravity. But in CFT, then like we know that we have, just like we know that at the end of the day, we have to couple the quantum field theory to gravity. In the CFT side, it's basically that statement is basically we know the stress tensor is there. It's not that like we can study quantities that decouples from the stress tensor, but that does not mean that stress tensor is not there. So in that sense, like just to include the effect of the stress tensor is kind of like from the CFT side, it's trivial. Like we know how everything goes. So it's not that I'll be able to tell you that no, the gravity has to be there. That statement probably I'll not be able to make.
I see. Yeah, I was wondering even more strongly. Sometimes people study these funny CFTs without a stress tensor, just by studying quantum field theory in fixed ADS, for instance.
Yeah, that's right.
And will all your axioms apply for such systems, or will they only apply for more genuine CFTs?
Okay, let me say it this way. So since at the end of the day, I'm going to assume CFT axioms, so it has to be a well-behaved CFT. That means there has to be a stress tensor. Like that's the reverse statement.
Part of your assumptions. Okay, thank you.
Yeah. So the one way you can think about it is basically like even I'm not going to use that assumption like explicitly. It's basically it should be in part of it should be a part of our thinking that since I'm assuming that it's a well-behaved CFT, that means like the stress tensor has to be there. Like I'm not going to use that statement anywhere where I'm just studying effective field theory.
Thank you.
Or probably like the statement is like whatever the dual CFT is, so it is part of a bigger CFT where the stress tensor is there.
Okay. Yeah. Thank you.
And more precisely, this is the kind of interactions that I'm going to study today. It's basically scalar field theory with higher derivative interactions, higher derivative 4-point interactions. And I'll show you these interactions must obey certain positivity, monotonicity, and lock convexity conditions at tree level. Otherwise, these effective field theories, they will be in the Swampland. And as I said before, and then I can take the large radius limit to recover flat space bounds. And there might be some subtleties. If I have time, I'll actually discuss that. But generally, like for this kind of interactions, the flat space limit is actually kind of straightforward.
And I'm really sorry, of course I should wait, but will you be able to put any bounds on the magnitude of mu k?
Yeah, that's exactly what. By magnitude, you mean like related to each other? Yes.
I mean, yeah, okay. Should be less than something or greater than something or whatever.
Related to that question is basically generally like when this kind of, the way you can generate this kind of interaction, you have some massive exchange and then you integrate out that massive state. So you get this kind of high derivative interaction. And generally, whenever you do that, so you get a cutoff scale from the mass of that exchange particle. And when you increase the number of derivatives, they are always suppressed by higher and higher power of that mass.
Right.
But that's when we study examples. The goal would be to actually derive that from consistency conditions. That like whenever you have high derivatives, they are suppressed by some kind of cutoff scale.
Yeah, I understand. But just to relate it, if you had derived it by integrating out a massive particle, mu k, as you say, would be related to that mass. So now to turn it around, are you able to put a bound on the magnitude of mu k, which in effect, let's say, would be a bound on the ultraviolet scale?
No, that because like we are working within the regime of validity of the effective field theory, like we don't know where it is going to break down. Only thing that you'll be able to say that there is some cutoff. So
you can't say whether it's the Planck scale or whether it's 10 times the Planck scale or anything.
No, basically, since there are like multiple this high derivative terms, what you can do, you can basically relate the cutoff scale of all of them.
Okay. So you sorry, you should go on. So you relate the coefficient of k equals 1 to k equals 2 or something like this in suitable units.
That's the main goal. Like it's not that will be possible for all interactions, but that's the main goal, like to derive those kind of bounds. Yes.
All right. Thank you.
Another goal would be, as we have already discussed, to derive or to figure out whether these assumptions about the scattering to scattering amplitude, whether they're valid or not directly from conformal bootstrap. That would be a long-term goal. And I'll be able to say a couple of things about this, about the validity of these assumptions just from the example that we're going to study today. This is the outline of the talk. I'm not sure if I'll be able to cover the fourth one. Let's see. I'll just try to cover as much as I can. Let's pause for questions if there is any more questions before I move on. Okay, so this is the setup. So I'm going to study this very specific scalar effective field theory in ADS. So I have this kinetic term. I also have a mass term. And I have all these high derivative interactions. So mu is some overall coupling constant. And then there is this lambda coupling constants. And then I have basically like an infinite tower of these high derivative interactions.
Sorry, Sandipan, is there a specific reason you picked this subset of higher derivative contact terms? I mean, there is a double infinity worth of higher derivative contact terms, right?
So I'm going to discuss that. So okay. So they're basically like these dots are important. Yes.
Okay. Sure.
Okay. So assumptions. The first assumption that I'm going to make is basically there is no dynamical gravity to begin with. So this is just for simplification. I'm going to include gravity as a generalization, but just to give you a brief overview of the main argument, first I'm going to assume there is no dynamical gravity. The next assumption is everything is everything will be analyzed at tree level. So that will be implemented by taking this mu to be small. So everything will be computed at the leading order in mu. the third assumption is basically I'm going to take R radius to be large. And what I mean is basically the cutoff scale of the effective field theory, which let me call it M, whatever that cutoff scale is. So R radius times M is very, very large. Another assumption that...
Sorry, but little m could be order R radius.
Yeah, little m can be anything. Yes. Yeah. I'm not making an assumption about little m.
So, and could in particular be 0, right, Sandipan?
Yes. So the reason, first I'm going to discuss the case where like m square is non-zero for a like just to show you something. But yeah, in the argument for me, I don't actually care if m square, even I can take m square to be negative. So that because it's in ADS. So yeah, there is, depending on what you are like how you choose your m square, you might get different set of bounds. But in principle, there is, yeah, you can study all these limits.
Right.
And the thing that actually we definitely need is basically the assumption that even in these dots that there are no light particle with spin greater than 2. So that's actually very important for us. But there can be like other scalar particle, other spin 1 particle, like everything else can be there, but there are no light higher spin particle.
Light means what, Sandeep?
Below, like there is no if this big M is the cutoff scale, even if there are like higher spin particles, their mass is above that cutoff scale.
Thank you.
Sorry, Sandipan, but of course, as you know very, very well, if you had a finite number of light high spin particles with spin greater than 2, that would violate the chaos bound.
That's right. Yeah.
So
basically, yeah, even if you include high spin particles, they have to be a tower, and the tower, the lightest of them should be above this cutoff scale M.
Right. So if you allow for a finite number of light high spin particles, you immediately conclude they cannot.
Yeah, that's right. In this, from this argument, I can do that. Yeah, that's right. Yeah, actually, yeah, that's a good point. I don't actually have to assume that. Yeah, that's a good point. Yeah, that's right. And also, there can be phi cube interactions. So the phi cube interactions, they are basically in these dots. The important point is whatever bound I'm going to derive today, they should not depend on like whatever else in the theory. So even if there are this phi cube interaction, if I'm not going to actually like compute the effect of the phi cube interaction, but all the bounds that I'm going to derive, they are independent of this extra things that you can write down. And the other point that we discussed few minutes back, it's basically if you even at the level of 4-point interaction, if you have a lot of derivatives, I think whenever you have 12 or more derivatives, you can write down interactions which are different from this phi square box K phi square, this kind of interaction. So basically, all those other interactions, in some sense, they are subletting. So what I mean by that is basically whenever I'm going to derive bounds, they are independent of those other interactions. So even if they are present, they are not going to change the bounds on lambda K that I'm going to derive today. Said in a different way, any four-field interaction with derivatives, as many derivatives as you like, they can be written as a sum over this kind of like phi square box K phi square interaction plus interactions which are orthogonal to this kind of interactions. So because of that, whatever statement that I make about phi square box K phi square, they are independent of those other all those other interactions which are orthogonal and in some sense subletting, because they are actually subletting. Another way of saying that they are subletting is basically this. If you take the forward limit, this is the interactions that will give you a non-vanishing amplitude in the forward limit.
Sandipan, one question.
Yes.
The assumption 2, is it a non-trivial one, or I mean, because you are assuming that the effective theory is weakly coupled, is it something that I can tune a priori? Because once I integrate out the massive particles, I get what I get. It's not clear whether I will get it to be weakly coupled, right? Or is it?
That's right. So basically, it's kind of like a statement about tree-level UV completion in some sense, yes. But this is again a technical assumption. So for conceptually, even if somebody wants to include loops, conceptually, the argument is exactly the same. It's basically like when I'm computing Witten diagrams, I'm just computing tree-level Witten diagrams. But the CFT arguments that I'm going to make, they don't care about like what you are assuming about the effective filter. They are general CFT statements. So it's basically like if somebody wants, they can like compute as many loops as they want, and then they can just go and use the CFT theorem to find out like how the bounds are changing when we are including loops.
Yeah.
Sorry, I slightly missed that answer, but I had something similar, which is if you took higher polynomials in phi, they could contribute through loops, right? And you're saying that, is it that you're assuming that they're not there, or is it that if they were there, it won't change your arguments about?
No, loops. So the argument will be the same, but bound that they can affect the bound. So basically, okay, let me say it this way. So even if you have like other polynomials in phi, so if you can basically, not always, but for the massive case at least, what you can do, you can basically like package everything in this, like since I'm going to study 4-point scattering amplitude anyway, you can package everything in this lambda case. So I'm going to
package means the additional couplings won't change the bounds on these couplings, or there is a field definition. What does that mean? Sorry, I didn't understand.
Basically, what I mean is basically like what I mean by lambda k might change. So the statements that I'm going to make, the bounds that I'm going to make is about the lambda k. But if you have those kind of loops, probably they are going to change what your lambda k is, but they are not going to change these bounds.
So this I should think of quantum effective action.
Yes, that's right. Yes. Yeah.
Then I see. It's a local quantum effective action obtained by integrating out the higher polynomials of what could be a massless field if m were 0. Is it? I mean, I don't understand that comment then.
Yeah, this is basically an effective filter for the 4-point scattering amplitude, like that, nothing more than that.
Then the terms will be suppressed by 1 over little m square.
Not
because you have integrated out loops including phi, I would think.
Okay, so that's why basically I introduced this parameter mu. So it's basically like everything. This is an overall coupling constant. It's basically like it's there. One way to think about it is basically that this mu coupling constant is there for like all the other interactions as well. So when you include loops, everything is like order mu square. But the statements that I'm going to make, that they will be at the order mu, not mu square.
So I guess what one way of saying what you're saying, is this true that when you integrate just the massive particles, the interactions of phi that you generate have a very small coupling constant in front of them.
That's
so
right.
If you have phi to the 7, it will have a very small coefficient in front of it, and then the resulting quantum terms would have this extra mu in front of them.
That's
Even
right.
though they will be suppressed by the mass of phi itself, it will have a small coefficient in front of them. So that's what lets you neglect them, right?
Yeah. So an analogy would be like, you can think of this mu as the like string coupling constant. So that's kind of like one of the motivation of like thinking about the tree level effective action.
Mm-hmm. Okay.
Mm-hmm. Actually, this is a non-trivial point in the sense, like if you go back and look at the proof of the 4DA theorem, this is like this same issue or this same problem is already there. So because like even there, when you compute like 4-point scattering amplitude, you can always include loops, and whatever bound you derive, like that's basically for the full 4-point amplitude. So it's basically there is always some kind of like cutoff scale, and you are basically always expanding in powers of the cutoff scale or powers of the coupling constant, something like that. We are assuming that we are always doing.
Okay, thank you.
And then the next step is, as I said, since this is in ADS, thanks to Himskirk, Penrones, Kulchinsky, and Sully, we know that there is a dual CFT description in one less space-time dimension. And this follows from a very nice observation that they made. The observation is that there is a one-to-one correspondence between scalar effective field theories in ADS and perturbative solutions of crossing symmetry in CFT in one less dimension. So this is basically a scalar version of ADS CFT derived directly from conformal bootstrap, but at the level of 4-point correlators. And because like this is just like standard ADS CFT, the duality is all the features of this duality we are very familiar with. For example, for the scalar field in ADS, there is a scalar primary operator O in the dual CFT with the dimension that we already know from ADS CFT. And then since we're studying effective field theory in an ADS background, so there is no dynamical gravity. So we are going to implement that by taking the central charge Ct to infinity. Ct is defined as follows. So if you take Tt 2-point function where T is the stress tensor, in CFT, it has the following form. So it has some number, which is known as the central charge. And then there is some known tensor structure. Let me just write it I mu nu. And then basically some known power of the distance between 2 points. So this Ct is the central charge that I'm talking about. So the way you implement the fact that there is no dynamical gravity, you take Ct to be infinitely large, but you keep the cutoff scale m times r radius large but fixed. So that gives us the CFT gap scale.
Sir, can I ask a question, Sandipan, about point 3? So
Yes.
How should I understand this Ct going to infinity limit? Is it that there is a family of CFT with increasing value of Ct, and in the limit Ct going to infinity, I'm supposed to get a CFT that is dual to the effective field theory that you write in the bulk? Because that seems too optimistic that such a family of CFT should exist.
I think I'm saying something a lot more trivial. It's basically that whenever we compute any quantity in CFT, I'm expanding in the central charge. I'm only keeping the leading quantity in the central charge. So basically, it's basically an expansion in 1 over Ct. I'm just keeping the leading term. And a related statement is basically
but that you could do only if Ct is large, right? So at least there may not be a family of CFT, but there exists somehow a CFT with, I mean, you see, right, there is some assumption here that there exists a CFT which is precisely dual to your effective field theory if you take Ct to be large. Is this something that is bound to exist? Sorry for
I think like this is not it's more like if you have this ADS effective field theory, the dual CFT will have this property. It's not that like like the existence follows from the fact that this dual, like there is like, okay, this is said in a different way. So if I just look at CFT crossing equations and like the consistency conditions, this is a like completely well-defined thing that you can do there. So in that sense, it does exist.
No, but is it in the spirit of this swampland kind of business that you write down some effective field theory in the bulk? It's a priori not clear whether you can couple it to gravity even weakly, right? And in the point 3, you are essentially assuming that it can be done. It can be coupled to gravity weakly.
Yes.
So this is clear that in any effective field theory, you can couple to gravity even weakly.
Okay, so that's a fair point. So so you're kind of saying, is there an implicit assumption that all the like in this kind of language, it's not just that we are deriving constraint on the effective field theory. We are making an implicit assumption that effective field theory can be coupled to a graviton. Yeah, okay. So that assumption is there. Yes, that's right. So if this duality is kind of, in this duality, that assumption is basically almost inbuilt.
Okay, thanks.
Hi, Sandipan. You're using the CT large to ignore the tree, for instance, the tree level exchange of gravitons, right?
Yeah, that's right. Yes, yeah.
But in, let's say, the dual of n equals 4 Yang-Mills, the tree level exchange of scalars is of the same magnitude as the tree level exchange of gravitons.
Yes, yeah.
So you're assuming that the coupling of scalars to themselves, while small, is larger than the couplings of scalars to gravitons.
That's right. Yeah.
And do we have an example of such a?
This is the example. Probably. The way to think about it is basically like, this is like, since like we know everything about this dual CFT, so this is a generalized free CFT is an example of that.
I see. No, but I meant some CFT that was independently defined, that had an ADS known dual that.
I mean, even for generalized CFT, it's not clear. The previous point, the question that I asked would hold, right? I think. Sorry, Shiraj,
yeah. No. I mean, similar to what you're saying. I'm just saying that in G string small, we have such examples, right? N equals 4.
Yeah.
But now you're requiring more, right? You're requiring a second hierarchy.
That's right. So it's basically, that's because like, it's kind, I think this is just technical simplification, because like that, for me, it's easier to include gravity than to like not include dynamical gravity. So the way to study effective field theory in ADS in this kind of language is basically like, you have to have those kind of hierarchies. Like basically you'll be able to tune M-Planck to be like infinitely large first, then you do everything else.
No, but I'm happy to tune M-Planck to be infinitely large. But when we did that in n equals 4 Yang-Mills, let's say we take one of the scalars, let's say some dimension 2 scalar. Yeah. It's the 4-point coupling of what you get from exchanging the dynamical scalar is of the same magnitude as what you get from exchanging gravitons, right? So that's not the same as M-Planck going. Removing gravity and keeping the scalar interactions was not the same as M-Planck goes to infinity. Right?
So generalized free CFTs, in that sense, they are different from the like n equals 4 super Yang-Mills, things like that, because like this kind of like these generalized free CFTs, they are kind of defined with the help of this like scalar effective field theory in ADS. So in that sense, they are kind of like, they are by definition like
but then I'm just going to go back to Abhijit's question. It's not clear a priori that such theories can be made into full CFTs, right? Right, because you'd have to do quantum loops in the bulk and define all of that. So I mean, then if you're going to use some CFT theorems, that sounds a little strange, right? I mean, if you're going to say that removing gravity is a technical assumption that later you will fix by including gravity also, then it's totally fair.
Yeah, I'm good. Yeah,
that's exactly. There is no question from my side. You will add, this is just some technical, easier to do it without gravity, and you will later include gravity. That's fine.
That's what I said. Like in this kind of approach, like inclusion of gravity is easier. Like it's basically, I'm kind of forcing like the gravity out of the
technical first, as a toy model for the real problem.
Yeah, that's right. Yeah.
Okay, fine. Yeah, thank you.
Yeah.
Can I ask all of you the following, that is it possible, Sandipan, that what you had in mind was a situation where there is a mass scale m, which is parametrically smaller, let's say, than M-Planck? Now, of course, exactly how to achieve that, whether you can, that's another question. I agree completely. But at least to begin, there's some mass scale which is much smaller. Now you integrate out the particles at that scale, you get these couplings. And then your point is, I want to now take M Planck to go to infinity, keeping that mass scale fixed. That's sort of what you have in mind, right?
Yeah.
Okay.
And Sandeep, we have an example of that, right? We could just do weakly coupled string theory. And that mass scale then is the string scale.
Yeah, very good. Very good. Very
Okay.
good.
But in this example that you mentioned, it's not like, this is like what happens in AD S5 times S5. And there, because many of the scalar particles that remain light also had their origin in the 10-dimensional graviton. There was the interactions of scalars with themselves were as weak as the interactions of the scalars with the gravitons.
That's right. Yeah.
So it's even in the one example where it has some of the features of what you're saying, 0.3 was not true.
No, the point, okay, there are two things. We are basically talking about two different things here. So when I include dynamical gravity, like the situation that Shiraz is describing, that will be included in that picture. So this picture is more like, let's say, like I just have a theory where I have like two scalar field, one is massive and one is, let's say, massless. I'm just integrating over the massive, and there is a 3-point interaction between the light and the massive particle. I'm just integrating out the massive particle, and I have a low energy effective field theory. So even, can we say anything about that effective field theory just by looking at it? So yeah, and
no, but that you are assuming you're going to say things from CFT, right? So assuming that there is the good CFT description. So in particular, some stress tensor with large CT and so on, right? And that you just what you just said that was not referenced to.
Yeah.
Right? So yeah.
So as I said, like that.
The point.
Yeah, that in this kind of picture, that implicit assumption. Actually, I have to be careful here because this is so everything that I'm going to say, it basically is built upon this like dictionary between solutions of crossing symmetry and effective field theories in ADS. So even there, I have to be very careful that in that kind of dictionary, how important it was that there has to be a stress tensor. So I actually don't remember very well at this moment, but probably it wasn't that important.
No, I don't think it's important. It's only important if you're going to borrow things from CFT, assuming that it's a good CFT.
Yeah,
CFT axioms, right? I mean, so only then it would be important for you to make that in a honest CFT. But maybe, I don't know, would you be using crucially that the CFT has a stress tensor, or that is not going? That will
only
not be playing.
I'm going to use these are the two things that I'm going to use, and they are I think very mild assumptions. It's basically OP exists in CFT, and the second statement is basically the statement of unitarity that the OP coefficients are real. That's it.
No, but that does not quite require you to have stress tensor, right? I mean, that just,
as I said, like this is like stress tensor. Like philosophically, we need a stress tensor. Like nothing more than that. Like since I have a CFT, I know philosophically that there is a stress tensor, but like it's not. I don't have to use it whatsoever.
Yeah, and presumably Cauchy-Schwarz inequality or something like that. So that is also
not really, because like any Cauchy-Schwarz inequality that we have to use, they follow from like these two CFT conditions.
Yeah, okay, fine, thanks.
So okay, so let me say a couple of things about this generalized free CFT. So to do that, let's first make the ADS effective field theory completely free. In that case, like all CFT correlators in the dual CFT, they will factorize into 2-point correlators. So that's what I mean by a generalized free CFT. And even though we started with a single scalar primary operator O in this dual CFT, just from crossing alone, we know that there has to be other composite primary operators in the theory. So composite operators like this, where you have like the scalar primary operator O, but there are many derivatives. Like there are n boxes and there are L uncontracted derivatives. So these are the double trace operators, which are generally written in this notation with subscript n and L. So from crossing, we know that all such double trace operators have to be present in the theory for all even L, so 0, 2, 4, and all n, integer n, which non-negative integer n. And so this subscript n and L, they basically they tell you about the spin and the dimension of this double trace operator. So spin is L because you have L uncontracted derivatives, and the scaling dimension is given by the scaling dimension of the original operators plus 2n plus L. That's just from simple counting. Now, when I introduce interaction, what happens is that the dual CFT remains almost the same. The operators are exactly the same, and there are no new. It's not that you introduce new operators. What happens is basically these double trace operators or other multi-trace operators, they receive anomalous dimension. So they have their dimension, scaling dimension is basically what we had before, plus a small correction which comes from the interaction. And similarly, like some of the OP coefficients also get small correction from the interaction. Just to give you an example, when we include a 5 to the 4th interaction, what it does in the dual CFT is basically it gives anomalous dimension to only to spin 0 double trace operators. Like this. So now if I also include something like a phi square box square phi square interaction, that leads to anomalous dimension to to spin 2 double trace operators. Similarly, if I add something like phi square box 4 to phi square, I have anomalous dimension to spin 4 double trace operators. So there is a very nice connection. So for the theory that we are studying, so basically the dual is basically a slightly deformed generalized free CFT where the double trace operators now have this anomalous dimension. So the spin k anomalous dimension is proportional to lambda k over here. So that's a precise relationship at tree level. And
in the previous slide, the box squared was there. Did you want a box squared or just box?
You mean like here?
Yeah, in the second and third line.
Yeah, so yeah, it is box square, box 3 or 4. It's always like even number of.
Oh, okay, right, sir. Yeah.
So this relationship it's true only for even k. The reason is basically just from symmetry you can show that there are no odd spin double trace operators when you have identical operators. So that's why like there is a relation between something like box square, box 4 to those kind of interactions with box 6 with like gamma 2, gamma 4, things like that, gamma 6. And this is and another important point is that this proportionality constant is always negative. That's a very important point that will be useful later. Okay, so now the goal is to figure out when this effective field theory can be UV completed, or rather, since like I'm going to use conformal bootstrap. In conformal bootstrap, we don't actually say, we cannot say when a theory can be UV completed. We can only rule out theories. We can only say when it cannot be UV completed. So that's exactly what I'm going to do today. So I'm going to basically ask this dual question. I'm going to ask the question that when this scalar EFT in ADS cannot be embedded into a UV theory that is dual to a CFT obeying the usual CFT bootstrap axioms. So that's basically existence of OP and the fact that OP coefficients are real. That's it. And the way to do that is basically via this CFT theorem. This is a theorem about CFT Regi correlator. So okay, what we have is this normalized 4-point function, normalized by the 2-point functions. Where we have like 4 identical operators, but inside some correlator in Lorentzian signature. x minus and x plus, they are the standard, they are the null coordinates where this time is going in the upward direction. And the 4 points are shown in the figure. So this is the left Rindler wedge, this is the right Rindler wedge. So the way points are chosen such that like the operators on the left Rindler wedge, they are basically Rindler reflection of operators on the right Rindler wedge. That's how I'm going to choose 4 points. And whatever I'm going to say, that they are valid in any spacetime dimension. So this is basically only a 2D subspace of the full spacetime dimension. So all the points are restricted to a 2D subspace. Another important thing is that some of the operators, for example, these 2 operators and these 2 operators, they are time-like separated. So the operator ordering inside this correlator, that's important. And the operators are ordered as written. Okay, so the Reggie limit is taken in the following way. So we keep these 2 operators fixed. We keep these 2 operators fixed. We don't do, they are just somewhere on the on a special axis. Then we take OX1 and OX2. Oh, sorry.
Sorry, so you've anti-time ordered your operators. Is this right?
No, this is neither time ordered nor anti-time order. This is, let's see. Yeah, this is not.
Well,
this is X.
Well, I thought 2 was to the right of 3 and 4 was to the, sorry, 2 was to the left of 3 and 4 was to the left of 1.
Yeah, so
looks,
4. So this
like
is
everything in the past is to the left of everything in the future.
Let's see, O4, X. I don't see, because like this is the first one. Oh, sorry, I don't know. Okay, so this is the first one on the left. This is the second one on the left. This is the third one, and this is the 4th one. So this is not anti-time.
No, the only ordering that matters are those that are time-like related, right?
Yeah, that's right. So I can change 3 and 2.
Yeah.
Yes, that's right.
So the only question is whether what the relationship between 3 and 2. Oh, maybe. I see. So I was getting confused. So 3 and 2 are the 2 guys. So 3 is to the right of 2. So the future guy here was to the right of 2.
Yeah.
And here 1 was to the right of 4. Yeah. So it does look like anti-time ordered, right? The guy. Sorry, I'm sorry if it's a stupid question, but between 3 and 2, the earlier one was to the left.
Between 3 and 2, the earlier one on the left. Yes, that's right.
And once again, between 4 and 1, the earlier one was to the left.
4 and 1. Yeah, that's right. But like this is like time ordered individually. Yeah, that's right.
But no other ordering matters because all the rest are space-like separated.
That's true.
Therefore, it looks to me like you've anti-time ordered your operators.
Yeah, I think you can say that. Yeah, but yeah, it's not going to be important at all. But yeah, I think you can say that.
Just the complex conjugate of the usual Euclidean correlator.
No, this is not like usually. It depends by what you mean by usual correlator, because like the ordering of the usual correlator is the ordering of the correlator that you get from the Euclidean correlator that's actually different.
It's different because it's time ordered.
Not just that. So basically, if I write down the operator, that follows directly from like Euclidean OP. So that's going to be, let's see, that's going to be so this one. So this is the one.
In the last two, did you mean O2, O3? Sorry, did you mean O2 on the right and O3?
Yeah, that's right. Yeah.
O2 was extreme right and O3 was the second guy?
Let me write it again. I think this is. So this is,
I'm sorry to disrupt.
no, this is basically my iPad, I guess. Let me write it somewhere bigger actually. Okay, let me write it here. So this is basically OX, let me be X1, OX4, and OX2, OX3.
Sorry, there's something elementary I'm not understanding, Sandipan. I thought ordinary Euclidean correlators, when analytically continued, give you time-ordered correlators.
So basically, like in this Lorentzian figure, for like this is, I have a left and right interval. The easiest way to figure out which one comes from the Euclidean correlator is basically the one which is symmetric in the left and right. So basically, like the ordering in the left interval and the ordering in the right interval, when they're the same, so that basically that's the one that does not cross any branch cut.
Right. No, perhaps I'm just saying something more elementary. I'm saying, ordinary quantum field theory, not even necessarily a CFT.
Mm-hmm.
When we take Euclidean correlators and, analytically continue, we get time-ordered correlators, right?
Yeah.
So maybe I should say less simply. I'm saying that the I epsilon prescription that would give rise to this thing, is just a complex conjugate of the usual I epsilon prescription of Feynman.
No. I'm actually crossing a branch cut. So no.
Well,
So, basically probably like,
you're agreeing this is anti-time ordered, right? This is ordered in reverse. If I take ordinary time, X and T, not some Rindler time.
Okay.
Just ordinary time, Minkowskian time. You agree that this is anti-time ordered, or have I messed that up? Everything to the past is to the left and everything to the future is to the right.
Let's see. I think I agreed with that, but let's see.
Now, the usual I epsilon gives time-ordered correlators.
Yeah, that's right.
So this is just a complex conjugate of that, right? I mean, it seems to me that if you just take T to minus T, you've written time-ordered correlators. In the ordinary sense, not in some fancy Rindler sense. Maybe that's the confusion.
But I'm not going to use Rindler time. Okay, let's see.
I'm sorry, if this is not important, we can go on. But just...
you want it to be OTOC in the Rindler time, right?
That's right, yeah.
So which is correct. I mean, as Shiraz says, it is anti-time ordered, but in the Rindler time, it is OTOC. It is kind of OTOC that.
But this is also a fact that, as Shiraz said, like if I take the Euclidean time and perform an analytic continuation, then that should be trivial.
Well, I don't know about trivial. I'm not saying trivial. Maybe is a bad word. It's just the I epsilons are those of time anti-time order.
Okay. I think the problem, the confusion is basically like. So in CFT, the analytic continuation that I'm going to do, the thing that in my head is non-trivial is basically an analytic continuation in that row variable that people talk about in CFT. So that's kind of like the Rindler time.
Right.
So since I'm going to do analytic continuation in row variable, like from the Rindler perspective, it's going to look like I'm performing a non-trivial analytic continuation.
I completely agree.
Yeah. But if somebody chooses to start from the Euclidean one and just perform an analytic continuation in Euclidean time, then what you are saying is correct. Yes.
Okay, fine. So this is the same. This is a complex conjugate of in some sense, if you just take T to minus T, this is like the chaos bound configuration, right?
This is exactly like the chaos bound configuration.
Fine.
That's right.
Okay, great. Thank you.
Okay. So then I'm going to the Reggie limit that I'm going to take is the following. So I'm going to take the limit where the OX1 and OX2, they are going to infinity and they are approaching the light cone of each other at the same rate. So the way I'm going to implement that, basically the distance between, let's say this distance is some like eta times sigma. Similarly, this distance is eta times sigma. And so the distance of this point from the other light cone coordinate is 1 over sigma, as written here. So the Reggie limit, it's right here, is the limit where I take sigma to 0. And the theorem that one can write down is the following. So I'm not going to write down a general theorem for any CFT Regi correlator. I'm going to write down a theorem for a Regi correlator which has this particular form. So this is whatever I'm going to say next, they are valid only for when the Regi correlator has this very specific feature. So I have this one which comes from from the identity exchange that will always be there. And then I have this I, and it's basically an expansion in parts of 1 over sigma. So the coefficient is it can be a function of eta, but I have terms like 1 over sigma, 1 over sigma square, sigma cube, things like that.
Sorry, I forgot what eta was.
Eta is basically like so when I'm taking the limit that the operators are approaching the light cone, so and approaching infinity. So basically, it's basically some factor that which is there can be like some they are going to 0 or infinity at the same rate, but up to some like order 1 factor. So eta is that order 1 factor. One way to think about this is basically the light cone limit is basically eta going to 0, limit is the light cone limit. It's basically like for any practical purpose, I can just fix it to be some number. It does not matter, but like it's something that can be tuned.
Okay. Okay.
Probably
related to rho.
Rho, yeah. Or like if I'm being really vague, this eta is kind of like the impact parameter.
Okay, thank you.
And obviously, like from CFT, we know that this expansion should not be valid in general for all sigmas. So this is valid for when sigma is very, very small compared to eta and 1, but it's larger than some cutoff sigma star.
Sorry, Sandeep, but just to make sure I completely understand. Suppose we write the cross ratios as sigma e to the power rho and sigma e to the power minus rho. Z is sigma e to the power rho. And Z bar is sigma e to the power minus rho. Eta is sort of like rho, or it's some function of rho?
Yes. So okay, let me think a little bit. So you said Z is basically rho.
Sigma e to the power rho.
Sigma e to the power rho.
And Z bar is sigma e to the power minus rho.
Rho and minus rho. So in this language, the Regi limit is basically
sigma goes to 0 at fixed rho.
Yeah. So basically, eta. Okay. In the language I'm talking about, it's basically like eta is kind of like exponential minus rho. So that's eta.
Eta is e to the power minus rho. Fine. Thank you.
Yeah. Or minus 2 rho probably. So in my language, Z is sigma and Z bar is eta times sigma, something like that.
Okay. Thank you. Thank you very much.
Okay, so this sigma star is actually very important. So this is basically it's basically some kind of cutoff scale in this Regi expansion. So this is basically the quantity that's going to give us the cutoff scale in the effective field.
Sorry, why there are only odd powers? Sorry.
Yeah, that's actually very important. So I could actually start with both odd and even powers. Then just from like simple like consistency condition that CFT correlators must obey, we can actually show that all the even powers must vanish, because like this correlator satisfies a lot of like analyticity and positivity condition. The way to think about this is basically when we have identical operators in their OP, you can only get operators with even span. And so this is basically related to that. So the odd spin terms or what terms like 1 over sigma square, 1 over sigma to the power 4 that I'm dropping, they are basically contributions that can come from like an odd spin exchange. So since odd spin exchanges are not there, you can actually just from simple consistency condition, you can just rule them out to begin with.
Okay.
Sorry, Sandipan, since you, I'm very confused. What exactly is that equation? Z equals sigma e to the minus rho, z bar equal to sigma e to the plus rho. Is that right? What exactly is that?
Our notation that Shiraz likes.
Yeah, it's a z is equal to, my one is sigma e to the power rho, z is sigma e to the power rho, and z bar is sigma e to the power minus rho.
Okay.
Yeah.
But Jane, just to understand, sorry, please excuse me now that, I mean, the horizons will involve a simultaneous taking of sigma to 0 and rho to plus or minus infinity. The bifurcate horizon would involve keeping rho fixed and sigma to 0. What? I thought you were going along the horizons.
Yes, so I'm going to take just sigma to 0. That's it.
Okay, then that's just the center point.
There is a bit of a change in the coordinates. So
Yeah.
this sigma e to the power rho is termed as sigma here. So it becomes z bar is sigma e to the power minus 2 rho, and e to the power minus 2 rho is basically eta. So that's how it becomes sigma and eta sigma, I think.
Yes.
And Sandeep, we're talking about the conformal cross ratios associated with these points, not the locations of the points.
Yeah.
I think maybe that.
Yeah.
Okay, but when he was drawing the coordinates on that diagram, that was locations, I thought.
Yeah, so that's why I did not mention z and z bar here. So in this picture, I'm basically really taking it to the light cone, that, as you said.
Yeah, but my z and z bar were not the locations; they were the conformal cross ratios. So sorry for the confusion. Okay.
So, yeah,
Okay,
that's
maybe it's related to what Schumann also said. I can understand if that transformation is there. Go on, all of you. Go on, please.
Yeah, so basically, I'm not going to mention cross ratios at all in this talk because like that's going to make it more confusing. So basically, just forget about this relationship. Like that will make things.
Okay. Sorry. Go on, please.
Okay, so as I said, then from unitarity, crossing, and analyticity, which follow directly from just OP and unitarity, and the existence of OP and the fact that OP coefficients are real, or basically the statement like they follow from conformal block expansion, basically. In other words, we can write down basically a sum rule for these CL coefficients that's here. So this is a precise sum rule that one can write down.
Sorry, before you get to that, Sandeep, and maybe I can say one thing that may make it more intuitive for Sandeep. You know, Sandeep, what we could think of is 2 points in Minkowski space, and then boosted in a Rindler sense. Okay. So roughly speaking, up to the subtlety Schumann mentioned, roughly speaking, I think eta is where on the x-axis you choose to put the points before boosting them.
Yeah, that's right. Yeah, precisely.
And sigma is how much you boost them.
Yeah.
Or more to the point, sigma. The boost parameter is tau. Sigma is like e to the power tau.
Okay. So then in Sandipan's diagram, at least, the null coordinates x plus and minus would have been, what did you say is the x-axis? Sigma? And the boost, e to the boost, right?
Sigma was e to the boost, and eta was roughly where you started before boosting.
Yeah. Oh, eta. Okay. Yeah, that's the standard Rindler coordinate then.
Yeah.
Okay.
This is a Rindler picture. Yes, that's right.
So eta is like space, and sigma is like e to the power time in between.
Okay. I understand that coordinate. Thank you so much, Raz. Go ahead, please. I'm sorry.
Okay. So in this for this particular Reggie correlator, I can write down the sum rule for the CL coefficient. Just like the sum rule that one can write down for flat space scattering amplitude. So it's basically on the right hand side, I have something. I have an integral over sigma, but for this integral, I cannot use this form because this is valid only up to some cutoff scale. So it's not that I can actually compute the right hand side, but from this unitarity and crossing and analyticity properties that we can use from conformal bootstrap, I know that this quantity here is positive. So basically all these CL coefficients, they can be written as some positive integral. And what that implies is the following. So it implies some positivity, monotonicity, and log convexity condition for the CL coefficient. My screen is not changing.
Sorry, Sandipan, just on this screen, what is this 1 minus real part? Why do you have 1 there?
So this 1 is basically from the identity exchange. So
Okay,
since this is normalized, so that 1 is there, yeah.
I see. So that because you want only to focus on the double trace guys, you want to subtract the 1 out. Is that?
And also the positivity condition comes is true only for this subtracted quantity. So the correlator itself is not positive.
Okay.
Yeah, but somehow I'm not being able to change. Like I'm changing my screen in my iPad, but the zoom is not changing. So let's see.
Maybe try reconnecting.
Yeah.
Yeah, now it changed.
Okay, let's see. Okay, it might work. Let's see. Okay, so from this sum rule, I can write down the following condition for this CL coefficients.
Sorry, Sandipan, if you sort of go back one to the previous slide.
Yes.
This was some sort of Cauchy-Schwarz kind of inequality. It was 1 was sort of like 2-point function square, right?
Yes, that's right.
And so it's like 4-point function is less than 2-point function square.
Yeah, it's more like okay. So one way to think about this quantity is basically it's basically the difference between just taking the Euclidean correlator and basically going around the branch cut and computing the next square. So the difference is positive. That difference is positive. So for the Euclidean correlator, since like you can use like in the Reggie limit, basically everything drops out. So everything is basically suppressed by positive powers of sigma. So you basically get a 1.
Yeah, one which means 2-point function square, right?
Yeah, that's right. Yeah.
Right. So this is very similar to the kind of manipulations they did in the chaos bound paper. Right?
Yeah, this is basically a CFT version of the chaos bound.
Yeah, fine. Thank you.
So we can derive this positivity condition that all the CL coefficients, they have to be positive. Then there's a condition that there is a parametric suppression for higher and higher CL. So basically CL plus 2 is suppressed by CL times this small quantity sigma star square, where sigma star was the Reggie cutoff that I showed in the last slide. And there is this like very interesting nonlinear constraint that one can write down from the sum rule. It's basically the statement that the CL coefficients, they are a log convex function of this the spin L. And log convexity is basically actually a stronger statement than convexity. So this is actually a very strong restriction. Now the next thing that I have to do, now
Sorry, all those other statements, where do they come from? Sorry, if
it's basically just from this integral. So since I know I have CL as an integral of a positive function, and it's basically I know how to change L. And these are basically like very like easy like algebra that one can do to show that like this positivity is actually obvious because it's a positive quantity. Then you can just take the ratio of 2 and you can just do some manipulation to show that the next condition is true. And the third one is basically the statement that it's basically the Cauchy-Schwarz inequality for integrable function.
I see.
The sum rule is kind of non-trivial, but these 3 conditions, they are kind of a very trivial consequence of the sum rule.
Which is the sum rule? The sum rule is which one, please?
Yeah, this sum rule, yes.
This.
Yeah.
I see. And sorry, the sum rule was just some Fourier. I mean, where did that come? Sorry, it's probably obvious, but where did that come from?
I actually did not show the derivation. It's kind of like the way you like. Morally speaking, this is exactly the way you derive like the constraint on IR coupling constant. Like you start with some analytic condition. You have some IR quantity on one side. You have some UV quantity on the other side. So it's basically like a lot of steps went into deriving the sum rule.
It's like a dispersion relation. You're using analytic properties and manipulating contours.
Yeah. There is a contour, and then it is morally speaking, it's exactly equivalent to how you derive the positivity constraint in like all this like phi square box square phi square kind of things. It's exactly that kind of argument.
And what the dropping of the arc at infinity is justified by chaos bound?
No, actually, we don't have to. So since this is CFT, I don't actually have to assume anything. It's basically like, this is the statement that CFT Regi correlator, they are always bounded.
Fine.
So
Fine.
yeah, so that's why like only input is basically like I have like OP coefficient, OP, and basically OP coefficients are real. That's it.
Good. So you're allowed to drop the arc at infinity because of, as you say, what the thing people sometimes call the quantum chaos bound, right? That instead of, yeah, I understand what you're saying. Fine. There is, at some point you drop an arc at infinity, right? In deriving this.
Yeah. In this case, the arc is not at infinity. It's it's CFT. You can always like move it to some finite position. But yeah, it's basically like here actually you can make the argument such that you don't have to drop anything.
Oh.
So it's basically like, okay, I didn't actually wanted to go into the.
No, then please don't. I'm sorry for this. Please just carry on.
Yeah. But like in this kind of CFT dispersion relation, you can map everything into a like finite region, and then basically you don't actually have to drop. Like there is generally a line and a circle. Basically, circle gives you one part, the line gives you another part. Like you're not dropping anything. The statement that you are making is basically in this language, the statement that in this integral, like this quantity converges in the limit sigma, like even when sigma is small. So this, like when I'm taking sigma.
Thank you. So what I was thinking of as the arc at infinity was actually the small sigma. Well, there is no funny contribution near sigma 0.
Yeah, and since like the Regi correlators are bounded, like I don't care, like it's a like completely well-defined quantity.
I understand, and that right. That boundedness is the same as instead of S square growth, S growth, right? Yes. Yeah. That's the same statement, right? I understand. Thank you.
So if you take the analogy that sigma and S are basically kind of same thing, then yes, as I said in the beginning, that's why like people believe that probably like the S bound is true because from this kind, like here it has to be convergent.
Yes. Thank you. I understand. Thank you.
So Sandipan, what is this R and minus R?
Okay. Yeah, that's a very good point. It's basically like a very important feature of this kind of CFT argument is basically in this integral, basically R is any quantity that you choose, which is between like sigma star and eta. Actually, it does not matter like what actual value of R is. Actually, this integral is R independent. That's a very nice feature of this kind of integrals. So if your R is in this regime, the integral is independent of the cutoff. Integral is independent of the lower and upper cutoff of the integral. So like that R will not play any role anywhere.
Sir, what is the analogy with the S matrix then? Because there, your integral in this S matrix, where you use the S matrix spatial relation, you use it. The integral is from the scale M to infinity, right?
Okay, yeah. So the
like cutting this off at some large value.
Other end. It's basically the statement that when you do the flat space dispersion relation, on the right hand side you have an integral of the imaginary part of the amplitude. But imaginary part of the amplitude is basically it becomes non-zero only when like you have like either loops or like exchange of other particles. So like in that integral of imaginary part of the amplitude, you can actually change the lower limit to anywhere you like, because like as long as it's not
I see. Got it. Yeah. There is no cut there. Yeah.
Yes, that's right.
I see. Thanks.
Okay, so now the next step is probably the easy part of the argument is just to compute the Regi correlator for the scalar effective field theory that we are studying.
Sorry, but so far you have not made a connection to the S matrix, right? This is the CFT. So far it's CFT.
Yeah, I'm not going to actually make like an exact connection with the S matrix because the problem is like if I try to do that, so the regime in the CFT side where I have so much control, that does not actually map into a precise flat space scattering amplitude. So when I can map a CFT correlator to a precise flat space amplitude, there basically I don't have so much control on the CFT side. So the way I'm thinking about it is basically just think about the effective action, just derive bounds, and then basically like don't try to like figure out the amplitude from the CFT correlators. Like since I know the bounds on the effective action, then that translates like as an indirect connection. I can just say things about the amplitude.
So you're saying you're always working on this Reje sheet rather than on the scattering sheet, where there is a more. Yes. Okay.
Okay. Now let me just compute this Reje correlator from the effective action that I started with. So there are two types of diagram that can appear. One is basically this kind of exchange diagram. In the case I have a phi cube interaction. Plus there will be this all important contact diagrams for these high derivative interactions. And one can do this computation in the Reje limit, and it has the structure that we just studied. And obviously that's why we started with that theorem. And then I can just compute these CL coefficients for this effective action. And there is a very nice relationship between the CL coefficients and this lambda coupling constants. It's basically the CL coefficient. They are proportional to this lambda L coupling constants for even L. This part is important. It's proportional to lambda coefficients only for even L. The actual prefactor is not very important. The important fact is it's basically proportional. CL is proportional to lambda L.
Sorry, this prefactor in the eta going to what, zero limit, is it singular or not?
It's
so the bulk. Sorry, yeah.
No, it's non-singular. It's basically actually it goes to zero. But the ratio of two CLs, if you take the eta goes to zero limit, that's actually something which is finite.
No, but I was just trying to relate it to the bulk point singularity. So are we expecting some sort of a bulk point singularity?
I'm not going to see the bulk point singularity. We are in the Reje shade. Here, like the bulk point singularity is not in this shade. So eta goes to zero limit is more like taking like the impact parameter to be very large.
Okay.
So the odd spins, there are like odd interactions. That means like things like box cube, box fifth, those kind of interactions. They don't appear here. So basically, the only contribution they introduce is basically you have something like this. So for CL is proportional to lambda L, but up to a correction. So the correction term is basically the odd interaction, but that's suppressed by some higher power of R radius. That's why they are not important. So that's why, like from this argument, I'll only be able to constrain this odd the even interactions, not the odd interactions. And then since like CLs are proportional to lambda L, then the positivity, monodicity, and log convexity condition of CL coefficients, they translate into positivity, monodicity, and log convexity condition for the lambda coupling constants. Let me be more precise. Let me give you the example where the mass squared term is positive. It's not just positive. It's basically it does not scale with R radius. So that means basically m times R radius in the large R radius limit. This is actually very large. So there is a reason why I'm going to study this special case, because there is a difference between this case and the massless case, and that the difference is actually a very important one. So this is for any finite mass, and when I take the large R radius limit, the corresponding scaling dimension will be very large. When I do that, first I'll again get the positivity condition for all lambda coefficients for even k. So this is basically a generalization of the Adams et al. Statement. The second statement is all the higher order interactions, so the lambda k plus 2, with respect to lambda k, they are always suppressed by this quantity, sigma star square r radius to the power 4.
I forgot what sigma star was, please.
It was basically, let's see, it's basically in the Regi expansion. I assume that the Regi expansion is valid only up to some small sigma.
Okay.
So it's basically like, it's the analog of the EFT cutoff.
So the EFT cutoff was could be worded as the location where there is a cut.
Mm-hmm.
Is there something similar you can?
Because in CFT, the cuts and everything, they're fixed.
Yes. So it's something sort of different here, you say.
I can give you a corresponding statement actually. Okay, so the cutoff scale in scattering amplitude can be said in the following way. So it's basically, it's the point where imaginary part of the amplitude becomes non-zero.
Yes.
So in this language, it's basically the real part of the, like, if you remember the sum rule, there is that one and the real part in the sum rule. It's basically where the real part the sigma star is the point where real part of this correlator, it becomes defined from 1.
But so I'm really sorry, but it's not clear to me why there is a specific sigma where that becomes different from 1. Is that some log n assumption, or is there some assumption?
This is an analogy. Like, I don't actually have to assume that. It's basically sigma star. To me, sigma star is basically when this expansion breaks down. That's it. But like, if you like push me to like to give you a physical statement about sigma star, which is comparable to like a statement about the EFT cutoff scale, it's basically the statement that like where this real part of the correlator basically becomes different from 1.
Perhaps the sigma ranges from 0 to infinity.
0 to 1 in this case.
0 to 1. Okay, so how do we know that sigma star is not equal to 1?
So sigma star, actually, I can tell you how it should scale. It's basically, it's in the CFT language, it's gap scale square. So that's.
So suppose I took just some generals, a CFT like, I don't know, Wilson-Fisher theory, not something with a bulk theory. In that case, what would sigma star be? I mean, would it be different from 0 or 1? Or?
No, it's actually very difficult to say, because like my definition of sigma star is basically inbuilt into this Regi expansion. This kind of Regi expansion is not valid in general. So this kind of Regi expansion is basically kind of designed for like theories with EFT dual.
So I didn't understand. I thought you were just doing a small sigma expansion, right? Or not? What?
Yeah, small sigma expansion, but like that, like it's basically that expansion is not valid up to sigma goes to 0. Because like, as I said, like since Regi correlators are bounded, like this kind of expansion actually breaks down at some point.
Right.
So Sandipan, is it so even in your explicit example of the contact terms, where you have a low energy effective field theory available to you, you cannot compute this G explicitly, right? Because this particular cutoff will be seen only if you input into it that the EFT is valid up to scale n, right?
Exactly. Yeah.
So in that sense, the ignorance is translated here, but not in a precise way. Is that?
Yeah. So there, like there is no way I can say anything about sigma star from this kind of picture. It's basically sigma star is kind of like an effective field theory. I don't know where the cutoff is, but I know there is a cutoff scale somewhere.
But the relation between sigma star and M is also a theory specific relation, right? It's not a universal relation. Right?
Very good point. So that
have a tilde sign.
Yeah. So it's basically I can define a cutoff scale that might not be the same cutoff scale that somebody else can define from, let's say, just from starting from the fully complete theory. So that's why, like, okay, let me go back to the bounds that I was discussing. There are some bounds, for example, the positivity bound. This does not care about what your cutoff scale is. Yeah. So this kind of bounds, they will like they don't care how I define my cutoff scale.
No, but cutoff is usually defined as the next massive particle, right? The mass of the next massive particle.
but for that I need to know but I'm just writing down an effective field theory. Like I don't know what things I'm excluding.
Okay, fine.
So basically that's why there is this modernity condition that I wrote down here. So this is, you can think of that as my definition of the cutoff scale. So this is this is basically suppressed by sigma star square times some radius.
But is it the point that once you fix it, it is true once and for all the ratios?
With this definition, okay, and now you may say that, okay, I can define some other cutoff scale. So basically the modernity condition should be think of as if basically this is valid up to one single rescaling.
Okay, so is sigma star roughly arbitrary or there's a precise definition?
So sigma star is basically like, so as I was saying before, sigma star was basically something like 1 over delta gap square, where delta gap is in the CFT language is basically where the new states are appearing. So in that sense, basically that's why sigma star is scales like the 1 over m square of the cutoff scale m of the EFT.
I see. Yeah, but you know, I was just trying to understand. Given a CFT, do you have a precise definition of sigma star so that you could get it with numbers, or is it some?
It's basically it's kind of like so. Okay, since I was like when I started with the effective field theory, I actually did not tell you what the cutoff scale of that effective field theory was, because like there was no if all the coupling constants such as lambda, so they are not dimensionless, so they're dimensionful. So basically. So that's why even from the studying from the effective field theory, I don't even know where the cutoff scale is. It's kind of the similar statement from the CFT side as well. I know there has to be some cutoff scale, but I have no way to define what that cutoff scale is.
Even if you knew the full CFT?
No, if I know the full, like if you give me the full UV complete theory, then I know, obviously.
Then you know, and what feature of that full UV complete theory? I mean, just say again, what is, I've handed you the full CFT correlator. Then how will you find sigma star? Okay, so basically then, if I look at the Reggie limit of that correlator in that CFT, I'll see that it has this kind of expansion only in some regime. Like it's not that expansion will break down for some small sigma. And it's the first singularity in some complex plane or something.
Yeah, something like that. Yes, yeah.
Sorry, Shiraz, but sorry, in CFT correlators, singularities are very constrained, right? I mean, you're not supposed to have singularity at any place. So this is unlike your amplitude, where the precise M is a place where cut starts, right? So there is a very, even if you may not know that position, there is a, a priori, if you are given everything, then you can find out that M. But I guess maybe Shiraz's point is that because CFT singularity, you are not supposed to have singularity at any other point except the coincident points. You're not going to find a very sharp sigma star point.
No, you can actually. The reason is, if I know the full correlator, because generally how Reggie correlators are behave is basically when sigma is very close to 0, it's basically it's actually not an expansion in 1 over sigma. You can actually show that it's basically some plateau. But if I have the full correlator, you can actually very easily show from the correlator like there is an expansion in some regime, and that expansion is valid up to a very precise point. So for example, let's say like I can take a CFT theory, like just forget about like the dual EFT. I can just take a CFT where, okay, let's take the following example. In the EFT side, I take the simplest example where I have a single light scalar field and a heavy scalar field. So in the dual CFT, I can actually compute the Reggie correlator exactly. So if I take the Reggie correlator, you can actually show very easily, like when I expand the Reggie correlator, somewhere like for a very specific sigma star, above which I have this 1 over sigma square kind of expansion, and below which there is no such expansion.
No, because there is a singularity, or what?
No, it's basically just like functional expansion. Like it's basically like you can write down many functions where basically like the function is completely well defined, but it does not converge below sigma star. So that this kind of expansion, they don't convert below sigma star.
But doesn't that mean in the complex sigma plane, there is a singularity, a complex 1 over sigma plane, there is a singularity at that point or not?
No, it's not, because like this is basically a feature of the, like it's just the statement that the function is well behaved, but this expansion is not valid.
But I thought the radius of convergence of an expansion is the location of the first singularity in the complex plane. That's not true. Sorry.
So this is, actually, we are going into a different point. It's basically like this kind of Reggie expansion. They are, you can think of, they are not actually convergent expansion anyway. They are kind of like asymptotic series. So that's why like this. I didn't want to go into that because like there are subtleties around that issue. But yeah, you should know like in case by case, you can actually show where like this kind of expansion arises and things like that. You can actually show easily, but it's very hard to say anything general.
But then it sounds, if it's not convergent, it sounds to me there's no clear definition of sigma star. Not that it's very important point, but if you were saying it's a radius of convergence, then I understand. But if it's not the radius of convergence, what is it? The location of the first Borel singularity in the Borel resumplan? I mean, at the moment, it seems to me sigma star is some approximately defined notion.
Yeah, it's kind of like, yeah, this function which obviously can be Borel resum below sigma star. It's basically where you are doing the resummation in some sense.
Okay, so it's the location of the first singularity of the Borel resummation and 1 over sigma. Yeah,
something like that. But I actually did not try to make this precise because like the things that I've been studying here it's actually just from some scaling. You can argue that a sigma star is something that's basically that scale as like one of our EFT cutoff scale square.
Okay, excellent. So at the moment, I'm thinking of sigma stars being something rough, approximately defined.
Yeah, that's probably the best way to think about it. It's basically some scale that you can define from CFT that, and you can rescale it up to some order 1 numbers without changing anything. So I'll not be able to fix that order 1 number in a precise way. And I'm not going to even do that because it's basically all the bounds, most of the bounds are actually independent of what exact sigma star is, and the rest of the bounds, they are basically valid up to 1 rescaling. So that's inbuilt in these bounds. So in that case, if let's say like I give you some definition of sigma star, which is basically different from somebody else's definition of sigma star by like a factor of 2, that should not change all the bounds that I'm describing here.
Okay, thank you.
Somehow, I mean, what is a bit weird is that, you use CFT for its some nice properties, right? In position space, you have these nice bounds and everything. But at the same time, you want something that is not nice, namely the cut, right? To define it sharply. So that has fuzzled out. So that's it's a bit of a, you kind of, in getting that nice axiomatic properties, you're somehow, I don't know, but this is just a meta point.
Yeah, so actually that will come up again. So only way I can actually relate what I can actually say anything about this M is actually just by going into the flat space, like just the flat space effective field theory, derive bounds there, and see, compare those bounds with this bounds, and you will see that like this definition has basically you can actually identify with a very specific definition there. So if I did not have that flat space argument at all, then I had no way of knowing that like how to relate this M with the cutoff scale of the
Sorry, go ahead, please.
But sorry, I mean, just to talk about the flat space limit, what exactly is the content of the statement? I'm not understanding, because just dimensional analysis would tell you that lambda k over 2 over lambda k should be of order 1 over the mass to this power, where that is the underlying scale you're integrating out, right? So without anything else, I would have said dimensional analysis. What is the precise content? That it's k independent? Is that the precise statement?
The second step, it's basically, okay, so the point, like I guess the non-trivial point is, so I know that just in principle, I know that this lambda coefficients, they should be all 1 over m suppressed, and not just that. They should be like suppressed by higher and higher power. Right. But there is an coefficient in the numerator. There is no reason why that coefficient has to be order 1 for all of them.
No reason, but if you had a massive particle, you were integrating it out, that's what you would get, right?
Yeah, and but my goal is to actually derive that statement in general. Like I'm not assuming that I'm starting from that example. From those kind of examples, I know this is what should happen. The goal is to actually just within the context of effective field to derive that statement.
I see. Or is it that you're deriving more, that if you knew the ratio of lambda 6 over lambda 4, you could, in a way, as bounded by something, you could in a very precise way, even up to all constants, put a
Okay.
bound on lambda 8 over lambda 4 or lambda 6. Is it
Let-
something more, or is it just dimensional analysis? Because, just dimensional analysis modulo miracles would give you this bound up to numerical coefficients.
Not really. The reason is, okay, so let me state this, the second condition in a different way.
Sorry, but yeah.
First of all, like, let's say I can always make lambda 2 to be 1 because I can just absorb that in mu.
Okay. Mm-hmm.
So then let me write like everything else. Let's say lambda 4 is basically like 1 over m to the 4th times coefficients, let's say C4. Lambda 6 as 1 m to the power, I think 8, C6, things like that. Like so now C coefficients, they are basically dimensionless.
Mm-hmm.
So this statement is that C4 is less than 1, C6 is less than C4, this is C8. It's basically like that.
No, sorry, but all with the coefficient alpha in front, right? Because which is undetermined, because this sigma relation between m, it comes with a tilde. So a priori there is a, I mean, why 1? Why do you write 1 is less than C4 and why not 1 is less than some alpha times C4 where alpha is not known?
For what's alpha?
Sorry, I mean this relation between sigma star and m comes with a tilde sign, right? It's not a precise equality, right? The relation between sigma and m is not a precise equality.
This m is a definition. Like I'm defining this quantity to be m. Like so that's the defined point. How it's related to the cutoff scale, like the one definition of cutoff scale in the flat space argument. That's a different issue. Like this is my definition of m.
Okay, fine. So even if you define it with the m, I mean, in some sense, I mean, you will not, if in some experiment I keep on getting these numbers, I will never be able to say, okay, this is violating the bound, because I can always absorb all that away in the m.
Not really. Like this, as I said, like this is up to 1 rescaling. So
but let's say I get a C6 which is 100, which is a dimensionless number which is 100, but I can say that, okay, that m that I was thinking about is probably bigger or whatever, smaller, right? And maybe you're saying from that I should get a bound on m or something. That's how I should think about it.
That's the point I'm making. If you just have C6, probably this bound is not important. But let's say you have C4, C6, C8, all of them. So then basically
all of them.
Yeah, if let's say one of them violate the bound, I can always rescale the cutoff scale such that that bound is not violated. But when you fix that rescaling, then there is no more rescaling left. Then
why? I mean, if I get even more violation later, I can even absorb that away.
No, it's for all functions you will not be able, like it's not. I'm not saying that like you.
In other words, look at the biggest number that I get in my experiment in this series, and just absorb that big number away, right? And then would it not work? Or
it's not just that, because like it's not just one number. Like there is a relationship between individual coefficients. So if you like, I can actually like I don't remember the example right now. Like I can actually write down functions which like you can tune one of them to be the right one. Then you'll see that like you are not actually being able to like satisfy other conditions. So that happens. Like there are simple examples for that happens. But I agree. Like naively, one may just conclude like this is violating the bound just by looking at one bound. But that's not the right way of looking at it. Looking at this.
Maybe the C's grow faster than exponentially in it. You cannot absorb it away by rescaling.
Right. So then I would agree.
Yeah. So you can make a similar statement. Yes, that's right. You can make a precise statement of that sort. Yes.
But that again is weaker than what you would have ideally like to say, right? Because and anyway in the experiment you would get some finite number of C's. Let's say you will get some finite number of C's. You will compute the ratios of lambda k by 2 or ck by 2 divided by ck, and you will go get those ratios. And whatever is the biggest ratio, you can just absorb that, and then everything will hold, right?
Yeah. So as he has said, like if you have finite number of them, like I'm not like this monotonicity condition. I agree. This is not very constraining. But this is not the only constraint that you can write down on the C coefficients. For example, like the thing that I did not mention here, it's basically, okay, there is the other condition. What happened? Okay, yeah. So then there is this log convexity condition. So you have, like, this one is also independent of the cutoff scale.
I see. So here there is no reference. This is a precise one, right?
So this is basically a very strong statement that this lambda coefficient, they have to be a log convex function.
Okay.
So just like, if I just had the monotonicity condition, I would agree that probably like you can find out different ways to actually make them consistent, but I doubt that, like, if you have even like 4 or 5 conditions, even then it's not that easy to do actually. Like I kind of checked by hand for a couple of examples, just by taking functions just to check that. But then since like we have this log convexity and positivity conditions, then it's actually combining all of them is actually very constraining.
Sorry, but these lambdas have different dimensions, right? Lambda.
Yes, but like if you take the ratios are basically like these are defined exactly such way, like you can introduce some kind of scale if you like, that will cancel out.
I didn't understand. So lambda k1 divided by lambda k2 has some power of dimension, and lambda k1 divided by lambda k3 has some other power of dimension. Oh, yeah. but because of the coefficients, k1 minus k. I see. I see. Yeah. Oh, thank you. Yes.
So these are basically, actually, yeah, this is basically, that's why this is cutoff independent, right? Like I could start it with coupling constants which are dimensionless, then like I'll get the exactly same relationship.
Sorry, I didn't understand, Shiraz, what you said, because you know, log m will always hang around unless your k1 minus k2 and k1 minus k3 is the same, right? Or not?
No, but look at the denominators.
Yeah.
That so one of them will have m to the power k1 minus k2, and that cancels with the denominator.
Yeah, precisely. Yeah, that's right.
But okay, so finally I'll get everything cut off independent.
That's right. Yes. Yeah.
Okay.
And more like pictorially, this is basically what like this bounds is telling us, like that these lambda coefficients for like even interactions, they are basically this kind of like positive decreasing log convex functions of integer and even k.
So this log convexity does not come out of the standard dispersion relation analysis in the flat space, right? This is something that happens only in CFT.
No, it does. For some reason, nobody actually wrote it down. But actually, yeah, I'm going to show you that. Like it actually follows. Okay. I don't know why nobody like wrote it down, because this is actually a very, very nice kind of constraint that one.
Right.
And okay, let me make one more point that these bounds are valid even in the flat space limit, since like this is a Regge correlator. So basically, this is a high energy scattering in ADS. So there is no reason why it should break down, as long as the flat space limit is well defined. Okay.
Sorry. What was the plot? It's
the schematically like how this lambda coupling constants they must behave. So it's basically like a pictorial representation of like the bounds that I showed here.
I see. So that was one of the examples. Like that was not the
any log convex function. Basically, they look like this.
They look like this. Okay.
And sorry, just to understand, because we had that discussion about when loops can be suppressed because coupling constants are small. What precisely is the small parameter in flat space limit that ensures your log convexity relation, that the coupling constant in front of some higher dimension operator is small compared to what? So that loops are small.
So it's basically like this mu over here, which is the overall coupling constant.
Okay.
So it's basically the statement, everything, all the statements that I'm making, it's basically at the leading order in this mu.
But mu actually is a code word for the dimension full coupling in front of phi square, delta k, phi square. So just, if you don't mind, can you help me translate that into some dimensionless statement in the flat space limit, please? If you don't mind.
I actually, let's see if I can do this. Is there any way to actually do that? because like there is nothing to compare it with.
That's slightly, I mean, maybe you have some ratios, but that's slightly why I'm asking.
Probably like, I'm not going to, probably I'll not be able to give you a very precise statement. It's basically mu has a, is not dimensionless. So mu times the some part of cutoff scale is basically dimensionless. That quantity, basically I'm taking that quantity to be very small.
I see. Okay, thank you.
That's the only thing that I think I can say.
Okay. Thank you.
Well, what you really want to do is to make sure that loops are smaller than the tree exchanges, right?
Yeah.
So you could estimate what, let's say, a loop contribution to some dimension full coupling would scale like, and look at the tree contribution, and that ratio of that you want to say is very small.
Yeah, precisely. Yeah.
But quite often the loop, if it diverges because it's non-normalizable operators, will have to be cut off. And if you cut it off at m, then it's dimensionless numbers of order 1. I don't know.
I think he needs, as you said, Sandeep, that there are these two scales. So one of the cutoff scales is of order 1 over G string, which is implank, but the loops are getting cut off at order string scale.
Yeah, some suppression like that.
Yeah, I think he needs that.
Otherwise, I was worried,
that's basically, that's kind of inbuilt in like, for like just by writing down this effective action, basically I'm kind of assuming something like that. Yes.
I see. Okay, thank you for those comments. Sure.
Yeah, it's kind of, that's why I initially mentioned that this is basically like roughly the analogy is basically like mu is kind of like the string coupling. But it's, even though, so that's kind of the motivation. So if one wants to study something like gravity on 4 points carrying amplitude, actually this kind of structure is kind of already there. So that was like, I'm trying to write down an effective action which kind of mimic like what I'll probably get for 4 point gravity on amplitude.
But like in M theory, there would not be such a limit.
Yeah.
Right. I'm just saying as a contrast.
Yeah.
Okay. I understand now. Thank you so much.
Okay. Let me now. Actually, I'm way over time, so like I don't know when I should stop.
Sure. Go ahead. I mean, how long do you think you would need to finish?
I probably like in 15-20 minutes I can actually probably wrap things up. Like I'll be able to cover the most of the important things that I want to cover. Yeah.
All right. Go ahead.
So as we are discussing, how I defined some cutoff scale from CFT. Like, is there a way to actually match that with the cutoff scale in flat space scattering amplitude? Before I do that, like there is something interesting that we should always check if I can generate same bounds from the flat space matrix argument. So let's take now that the mass square is non-negative, so it can be or positive. And again, just take the standard assumption, make the standard assumption about analyticity, unitarity, crossing, and Prezi-boundedness. And from Adams et al., I can write down the dispersion relation for this lambda coupling constants. And just from this dispersion relation, it has structure. It has the same structure as the CFT sum rule that I wrote down. So the positivity, monotonicity, and log convexity, they follow directly from this dispersion relation. So for some reason, they nobody wrote down this constraint, but it just this is a standard exercise. There is nothing fancy going on. Now, but the thing is that if you look at the monotonicity condition, you get exactly m to the power 4th, where m is basically the lower limit of the integration here. So now this is the only way I can relate this effectively cutoff scale with the cutoff scale that I defined from the CFT sigma star. Otherwise, if I didn't have this argument, I wouldn't be able to do that. But there is something interesting, that there is actually something very non-trivial that I should emphasize very much. It's basically, if this argument is valid, like under this assumption, this argument is valid even for the massless case. So, but
and once again, the log convexity comes just by using the standard dispersion relation, expressing lambda as an integral over the cut, and using positivity of the integral, right?
Yeah, that's right. It's basically like Cauchy-Schwarz inequality.
Okay. Yeah. Thank you.
So, when the mass square is positive, it's basically like, if I exclude the massless case, the CFT bounds that I discussed and this expected bound, they are exactly the same. Like there is no discrepancy whatsoever. So I take that as a very strong evidence in favor of this assumptions, these flat space assumptions, at least for the massive external states. But there is a discrete difference between the massive and the massless case. So the flat space argument, the expertise with argument, that's valid even for the massless case. So basically, like if I assume the same assumptions, I get the same set of bounds. But that's not true for the CFT bounds. If I take the exact massless limit to begin with, I get a different set of bounds, and these bounds are weaker. So to me, that's kind of saying that these assumptions may not be valid for the massless external states.
Sorry, when you say massless, do you mean literally zero mass, or do you mean order RADS?
I'm coming to that. So obviously, it's always possible that like there might be some more sophisticated CFT argument that gives you stronger bounds which match with the flat space bound. That can happen, but like other than that, like there is a very important difference between the flat space result and the CFT result. In the massless case, actually, from the CFT perspective, the massless case actually very subtle in the sense there are many different ways you can take the massless limit. For example, I can start with m equals to 0 in the ADS effective field theory and then study that example. Or what I can do, I can take mass to be very small, then first take RADS to be large, and then take mass to 0. So the first possibility is basically just taking the mass to be 0 to begin with. Second one is basically just take mass to be small first, then take RADS to be large, then take the limit that mass is small. And the third is basically a combined version of this. I can just take m to 0, RADS to infinity together with the product fixed. So the bound agrees, the CFT bounds agrees with the flat space bound only for the second case. So when I don't take the exact massless limit, is basically I take mass to be small, then take the limit that mass is going to 0. But if I take mass to be 0 to begin with, or if I take the other limit where basically I'm taking mass to 0 and RADS to infinity at the same rate, then they don't match. And just to show you how they look like, I'm not going to explain it that much. So the positivity bound is actually exactly the same. It does not care about like if you have the massless external states or not. But the monotonicity and the log convexity conditions, they get not a correction basically, but what happens is basically now the lambda in the bound, you have to actually rescale these lambda coefficients by some known factors. These n factors are known, which is shown here. They are kind of ugly, but like just the point is we know them exactly. So basically, from the CFT argument, we get a bound which is basically not the flat space bound, but a rescaled version of that bound, which is weaker, strictly weaker. And let me make a couple of comments about, so to summarize the previous part is basically, so from the CFT argument, it looks like the massless and massive cases are kind of different, but from the flat space argument, if I trust all the assumptions, the massless and the massive cases are almost identical. Okay, so the inclusion of dynamical gravity is straightforward here because now
Sandipan, since this is so interesting, can I slow you down? Yeah. So can you understand in some sense, why that happened? I mean, is it not true that the scattering is happening inside some elevator, some small elevator for the case where the massless case?
Well, you mean like why? No, you can do that. It's basically it's actually a very technical point. Like there is physically, I don't have any reason. I cannot tell you why it's happening, but technically, what's going on is basically. So the CFT argument, the CFT theorem that I showed you is basically for some CL coefficient that I defined in CFT. So for the massive case, the relation between the CL coefficients and the coupling constants are actually very simple, and basically they are independent of the which k order you're looking at. But as soon as you make it massless, what happens that the overall factors, they have like a k dependency. So that's why even though the bounds look almost similar, because of those prefactors, they actually they show up in these bounds.
But it would be nice to understand which of the flat space assumptions. Suppose the flat space arguments were not true for some reason.
Yeah.
Then it must be that one of the assumptions was violated, right?
Yes.
Okay. And which would you suspect would be violated?
Oh, this is a very I have my naive guess would be the Reggie boundedness condition.
Even though your correlator, is behaved in the same way, right?
No, there are reasons actually that statement about the chaos bound means that the amplitude cannot grow faster than s. That statement has some caveat.
Yeah, I understand.
So probably we are being too naive to say that means basically the amplitude is fine. So there are actually, I can actually tell you in some 6D cases, I'll not be able to give you a very precise example, but there are some 6D cases where it looks like the Reggie boundedness condition is basically it can be saturated. So the statement that it goes slower than s square is too much. The statement might be it grows as either s square or weaker. So that kind of it's possible to get those kind of statements actually.
I see. Could it be that what's happening is that while this S statement is precise on the Reggie sheet, by the time you do the analytic continuation to the scattering sheet, that coefficient has changed? That the sigma power is a power which is a function of rho.
But I'm always in the Reggie sheet, so I'm not going to this.
Exactly. But the scattering amplitude, the flat space scattering is on the scattering sheet.
That's right.
So could it be that
that's possible? I'm that, and in fact, that can happen. Yeah, that's a possibility. But the thing that's actually still bothering me is basically, even without going into the scattering sheet, I can derive this bounds just from the Reggie sheet.
Perfect. But then you find that there is some funny factor between your flat space effective action coefficients and your CFT things.
Yes. Yeah.
And maybe the other way of interpreting that is that the thing that you naively think of as your flat space effective action coefficient, so the flat space S matrix, is not quite that. And that you see that by this. And on the other hand, on the scattering sheet, what you see is what you get, right? The coefficient of the rho singularity is the flat space S matrix. The flat space S matrix. So maybe what the factor you're finding is some indication that there is a subtlety in analytic continuation.
That might be true. I don't have a precise answer. That might be true, but even if that's the case, I can actually, if that's the case, I'll be surprised for the following reason. So then it will look like probably since all these bounds, they are precisely in the Reggie sheet. Yes. That might be a statement that probably the things that since I don't have this kind of analytic control in the scattering sheet, probably that means that in the scattering sheet, whatever argument I make, probably they might not be as precise as things that I do in the Reggie sheet.
Yeah. Okay. Sorry, it's a vague question. I'm sorry for disturbing.
Oh, actually,
can I make a comment? Sorry.
Yeah.
No, so it may also be related to the elevator comment that Shiraz made, because I think if you write down a Witten diagram where all the external guys are massive guys, meaning delta scales large, then you can do this Witten diagram with a saddle point where the internal point where all the particles meet is one point in ADS.
Mhm.
Okay, where you can actually approximate that space to be a flat space.
Mhm.
But this happened only because you took large delta limit, which is the flat space limit. But now if you have massless particles as external particles being part of the contact diagram, the contact Witten diagram, then you cannot take any such limit, because your deltas are in your case 1 and 3. Your deltas are never big. In the case 2, the way you do it is by taking delta big, saying that it's a saddle point and doing that saddle point and then taking the, but to begin with, there will not be a saddle point because there is nothing, no parameter that is big. So in that case, in the massless case, the only way of approaching flat space limit that, you know, I would think of is by hand, which is by going to the bulk point singularity. So that is the way you would tune your interaction to happen in an elevator. Otherwise, they will happen all over the place.
No, that's true. That's true. But the thing that kind of bothers me that is basically, if let's say I didn't know anything about scattering amplitude, I'm just studying like effective field theory in ADS. I'll just like naively study this effective field theory and I'll just derive bounds. And just by looking at the effective field theory, like there is like, to me, it like just taking the like RADS large limit should give you like a flat space version of that effective field theory. Like I don't see like how that naive thing can break down. But when I'm looking at the correlator and going to the like scattering sheet to compare it with the amplitude, like those kind of in those kind of like technical things, these kind of factors and like bounds they show up. Just from a naive perspective, like there should not be any difference between these two approaches. But if there is, then actually that's very interesting. Like if that's the exact case that's happening,
because I think there could be, right? Because, you know, the way you would get your effective action, right? That is an inherently ADS effective action, because the loops of your massive particles, which you integrated out, could be, you know, happening in positions which are far separated from each other. Right? That will not have any analog in flat space. So if you were to take the previous quantum action, the full UV complete action, put it in flat space, and then compute the effective field theory effective action for the low energy guys, could be discretely different from the ADS analog. Because just because the loops of these massive guys could happen in places which are separated in ADS, where you would see a geodesic propagation, a curved space propagation.
Yeah, that's true. But like even the massive guys, basically, like they are always like, see, if they don't scale with RADS, but the corresponding dimension, that's large, right? So that should show up in like this sigma star, right? So that actually like probably the first step that should be done. Actually, I've been thinking about this problem for a while. It's just taking that particular approach that I have like two light scalar field, one heavy scalar field. Let's take one massless scalar field and one like massive scalar field, and study the effective field theory in flat space and study the thing in ADS, and then integrate out it in ADS separately. Not like just don't take the flat space amplitude, just take the ADS thing and get out the heavy thing and just see what happened in the CFT side. Apparently, this example hasn't been done yet. So, but this can be actually done from here. From this example, actually, you can actually go to different sheets and just check what's going on.
No, but
I think this would be different. These answers would be different.
But sorry, you also need to know what's happening at arbitrarily high energies, right? If your assumption, if your worry is about the S square growth, less than S square growth, you need to know what's happening at very high energies. And that's something you cannot control with an effective field theory.
Not in that way. Like what I mean is different. It's basically like what might happen. It's basically like I'm not talking about that. This effective field theory. I'm talking about the ways you are deriving the bounds in the flat space argument. They are basically S square is basically just to drop the contour.
Yes.
So, but there it's possible that like it goes as just a square, not.
I understand. Yeah, I was wondering. Yeah. Sorry, I was wondering that if if there was some sort of iconalization that one could do in ADS, it's conceivable that because that the impact parameter becomes so large that it starts seeing the ADS scale, and that one could compute that it actually changes between flat space and ADS.
In fact, this was done in this paper by Wald van Ries and Komatsu and so on, where they compute an exchange diagram with massive field and the massive field. So massive external fields and massive internal fields. Okay, and there they observe that for some particular configurations of the massive fields, the saddle point is such that the two interaction points are on top of each other. And that's why you can approximate this as a flat space process. And then there is a different regime of cross ratios. It's some sort of a phase transition, if you wish, where the action for a large distance separation dominates, where x and y are distance separated by distances comparable to radius of ADS, and it's a one saddle point dominates, and in some region the other saddle point dominates. In fact, when the other saddle point dominates, its action is infinity in the large R limit. So there is just the flat space limit is just not defined. So for a large region of cross ratio space, it is defined and it is equal to the flat space, the standard flat space.
And that's just within ordinary Witten diagrams, you say?
Ordinary exchange Witten diagram, not even loops.
Yeah. Right. And something even more interesting, I mean, it could be that if you look at...
But these are low energy things, Siraj. I mean, mostly what they find is that this happens in low energy. The other saddle point that is obtained when the external guy is at low energies. But as Sandipan has this intuition, when there is a high energy process involved, it seems that the on top of each other configuration dominates all the time.
Right. But suppose we go to very high energies. So with not individual Witten diagrams are dominating, but some of ladders.
Yeah. Couldn't
that change? Because roughly, I mean, my guess would be that large S fixed T is going to higher and higher impact parameter.
Yeah.
So if you keep going to higher impact parameter, at some point you'll see that you're an ADS, right?
Okay. Yeah. So that would even be different. Yeah.
Yes, but let's see. So basically, you're saying that if I study, let's say, the flat space dispersion relation, not in flat space, but in ADS, then basically it's possible that the large S limit can actually be completely different in flat space.
I mean, you want to find a way of making it consistent that the chaos bound is obeyed in ADS. But
Froissart bound is obeyed in flat space.
Froissart bound obeyed in flat space, or even more dramatically, if Sandipan saying in some cases it's even S squared flat space.
No, I actually know, kind of know an example where it's S squared. So that's why, that example is, yeah.
Right. So if those two are, let's take for discussion that we expect the two to be true. A, that ADS obeys chaos bound. B, that flat space obeys some other bound. Yeah. We need an explanation for it, right?
Yeah, that's right.
And it somehow has to be something that sees ADS.
The problem is basically there is a technical problem why so far nobody has done it probably. It's basically where you can actually go, where you can actually connect the scattering amplitude with some regime of the CFT correlator. They are basically these bounds are not that strong. So where you have the chaos bound, they are basically cannot get the flat space scattering amplitude from that correlator. So it's a technical issue. Probably what might happen, there is a bigger regime in the impact in the CFT cross ratios where basically both of these things are true. You can actually have some solid analytic understanding of the correlator, and also you have the flat space limit. So, but I don't know of any such regime as of now.
Yeah. Sorry for interrupting. Yeah, please go on, Sandipan. Sorry.
Yeah. This is a very this is something I find fascinating. For example, I actually even the statement about the crossing symmetry of Kundu scattering amplitude. Apparently, there is no proof of that for massless external states. So, these kind of things are kind of all seems to be similar.
Yeah. So
Just
in
one.
some sense, I guess one way to say it is that if you say high energy, you would expect things to be on top of each other, but radial limit is not quite that because T is fixed and S is large. So long distances also contribute.
Not really, because radial limit is more like, okay, roughly speaking, radial limit is more like impact parameter scattering amplitude, where we are keeping the impact parameter to be small, but before that we are taking S to be large.
Well, but that may not work that way in gravity, right? I mean,
so yeah, definitely, yeah.
For instance, the naive statement in gravity is that everything becomes large. Even fixed angle becomes long distance because you make big black holes. At the very least, that will happen. At some point, the black hole will become size of ADS, and we'll know we are not in flat space.
Yeah, that's right.
But it could even be worse because, I mean, as Veneziano keeps telling us, in gravity, the B becomes larger and larger, right? At fixed S.
Yeah.
So I think that statement is a bit theory dependent.
Yeah. I agree. Yeah, that's right. Yeah.
And one universal thing about ADS CFT is that, at least in CFTs with a stress tensor, it has gravity. So it would be nice if the explanation involved gravity.
Yeah.
Yeah.
Okay. This is our good segue to including dynamical gravity. So in this language, it's basically I'm no longer taking the central charge city to be infinitely large. I'm taking large but finite, but it's still larger than delta gap. All I have to do now is basically just, I had the old diagrams. Now all I have to do, I have to just include one more diagrams, which is basically a single graviton exchange. Now again, I can compute these CL coefficients. They are exactly the same. Only difference is that there is now a contribution for L equals to 2 from gravity. All the other CL coefficients, they remain exactly the same. Only the L equals to 2 coefficient that receives a correction from G Newton. So that means the positivity, monotonicity, and log convexity conditions for these interactions, they remains valid for k greater than or equals to 4. They remains unchanged. There is nothing, they are exactly the same as before. They don't care whether there is dynamical gravity or not. But all bounds involving lambda2, which is basically the coefficient of phi square, box square, phi square. So in all those bounds, now there is a shift. So there is a shift by J Newton.
This is because gravity is spin 2, right? This is the one that is a
exactly, yeah. And the fact that this is positive is basically a statement that there is gravitational time delay, not advance. So that fixes the sign. And to give you an example, without dynamical gravity, we had the relation that lambda2 is positive. So for now, when you include gravity, we get this lower bound, which is basically the right-hand side is negative. So the one way to think about this, why lambda2 now can be a little bit negative, is the following. The positivity of lambda2 without dynamical gravity can be thought of as some kind of causality constraint, where negative lambda2 gives you some kind of time advance. So now when you have dynamical gravity, gravity introduces a time delay. So because of that, the contribution just from lambda2 is now allowed to be a little bit negative, because gravity will give you some time delay, and the thing that you need is basically the full time delay should be positive. So because of that, now lambda2 can be a little bit negative. Naively, this expression looks little, this n coefficient is basically some numerical factor that's known. I'm not going to write it down here. One thing we should check for the right hand, since R radius is in the numerator, one thing we should check whether this thing actually is finite or not. Actually, in the regime of in the CFT regime that we are looking at, we can actually write down this right hand side by this expression up to some order or factor that's not important. So basically, this quantity, even though it looks like there is R radius in the numerator, so it looks like it should grow a lot in the large array radius limit, it's basically this factor. It's basically some power of delta gap divided by central charge. Since we are always taking the central charge to be large first, then we take delta gap to be large. So the right hand side is always negative but small, even when we take larger radius limit. Another way of saying this is basically we take the large radius limit in the following way. So because of that, the right hand side is still small. So now there is something really interesting. This is also something that I find really fascinating. So when I take the flat space limit now obviously I can no longer give you a precise definition of the right hand side because the radius scale is there. But since I know that the right hand side is still small, so basically all I can say that in the flat space limit, in the flat space amplitude, is basically in the right hand side I'll have a small negative number, which is basically theory dependent, because since we cannot actually tell you exactly what that is from the CFT argument, it's most likely that this is theory dependent. But the important point is this lambda 2 coefficient can now be a little bit negative, and actually this is actually consistent with flat space arguments by Kranvort, Mazag, Rastelli, and Simon Duffin from earlier this year, where they derive similar statements in d greater than 4. So, but
they had precise statements, right? They had a
yeah. So from the flat space argument, you can actually have a precise statement, but like again, like it's precise up to definition of the cutoff scale. Like with that definition, like you can actually define your cutoff scale in different ways, or actually rescale your cutoff scale out. Then the numerical values will be different. But they have other bounds which are actually completely precise. Like there is no freedom of changing anything. But yeah,
this cutoff scale was not the first singularity on the scattering on the S matrix.
Their argument is it's a flat space argument. Like there is no like.
In flat space, if you look at the S matrix as a function of S and P.
Yeah.
The first place on the S axis where the singularity occurs.
Yeah.
I thought that was their aim. That was a sort of.
So the way they phrased it is basically the point where the imaginary part of the amplitude becomes non-zero. Yeah, that's their aim. I think as far as I remember, that was their aim.
Yes, so that's pretty precise, right? At least within their setup.
Yeah, but like this particular bound, I have to remember. I don't remember exactly their expression. So basically, they had some kind of exclusion plot, which basically depended on like other coupling constants, things like that. It's not that like they have lambda 2 is greater than something. Like they had a space of coupling constant and they excluded a region.
I see.
And I don't actually remember like if they had some statement like lambda 2 is greater than exactly something like that. I don't think they had a statement like that, but I can be wrong.
Thank you.
And their argument was then valid for d greater than 4, but these are like the CFT based argument.
But in lambda 2 direction, if you take the extreme point, then you can always say lambda 2 is greater than some negative number, right? In the lambda 3 direction, there is a triangle kind of thing, right?
Yeah.
So if you take the extreme point and then you say that is your negative value, absolute negative value.
I think you can do that, but I don't like the thing that I don't remember very well. That's why I don't want to actually comment. It's they made everything like dimensionless with respect to the cutoff scale. I don't remember like there were a couple of rescaling that they did. So I don't actually precisely remember. So that's why I don't want to comment that if they had a precise bound or not. So they definitely had a precise exclusion plot. That's for sure.
Yes.
And the CFT based argument is actually valid even for d equals to 4. So that's something that's different from their argument. And
you're explicitly doing just tree level, right?
Yes, yeah. Even they did tree level. Like their argument was completely tree level.
But the place where they excluded, where they didn't want to, the reason they didn't want d equals 4 is that they.
I could not hear you actually.
Oh, I'm sorry. The reason they excluded d equals 4 was because gravity.
I think.
Right.
Sorry, Shiraj, you freezing in that crucial time.
I'm sorry. Can you hear me now?
Yeah.
Okay, the reason they did not want d equals 4 was because gravity scattering amplitudes were infrared divergent, and so not well defined at d equals 4, right?
Yes,
That will be true for you as well. So you should not be able to bound a quantity that's not well defined.
And the thing, I guess that there is a difference basically. So it seems like, okay, I guess this difference is basically kind of a philosophical difference. So even like if I just look at the 4D effective action in ADS and just take the large array race limit, like all this like Reggie, like the fact that the Reggie scattering Reggie correlator is basically like a high energy scattering amplitude in ADS3. Those kind of things, they don't depend on the fact that like we're in ADS4 or not.
Right.
So if just from this perspective, I don't see like how this argument can actually break down. So okay, let me say it this way. It's kind of like a very specific IR regularization of the flat space amplitude, and everything, all the bounds are basically independent of that regularization. So in that sense, I think this should be valid. Like they also can do the same thing. They can just take d to be 4 plus epsilon and they take the epsilon goes to 0 limit, this kind of things. And I think they can actually recover a 4D bounds from their argument as well.
Right.
And this is basically that version of the argument.
Right, I agree. It sounds good.
Yeah. One thing I find really interesting. So this bound that lambda 2 has to be is basically can be a little bit negative. So that actually is very important because like let's say like if let's just try to do something similar to 4D A theorem, but in the effective action of like Margolds streamer, if I just also keep the dynamical gravity part, in that case basically the lambda 2 is still be proportional to delta A. In the way they derive their effective action, this should not change. But now I just have like gravitons hanging around. But it looks like this bound is telling us that then in that setup, the A theorem is not, it does not follow from this kind of argument. So this is actually, I don't have a solid answer. Like this observation itself seems really interesting to me. Like this is something that should be explored. That if I just like keep gravity, that just like I'm doing everything around flat space, but I just keeping the like graviton turning kinetic term and things like that. So does that change anything for the proof of the A theorem?
Yeah, so you're trying to prove an A theorem about RG flows of quantum field theory coupled to gravity.
Yeah, that's right. And that sounds like a precise, well-defined question. Like I don't see why that's not a well-defined question. And I actually conceptually it's exactly like what Zohar and Schumer did. It's basically just I have to also keep the graviton term. That's it.
Interesting. Yeah. Thank you.
And before I finish, let me make a couple of comments. Like this kind of things can be done even when you have multiple scalars. Like it's like computationally, it's exactly the same. Let me just mention two new things that happens when you have either multiple scalars or you have like spinning external states like graviton or things like that. You get the kind of bounds that I showed you here. You also get two new types of bounds. So you will get bounds for odd k interactions as well when you have multiple scalars or you have gravitons, things like that. And another new thing is basically there are more complicated nonlinear interference bounds that you can derive. So these are also for whenever you have like more than one field. And the reason, again, I want to stress these two new kinds of bounds because like when you have graviton scattering amplitude, and that was the main motivation behind this work that I want to, at some point, I want to constrain the graviton 4-point scattering amplitude. These new kinds of bounds will actually play a very important role. Let me skip the application part. Like this kind of bounds has application for RG flows with global symmetry breaking. I'm not going to.
Can I ask one question? Sorry, just going back a little bit. So in your setup, you assume that the only a particular set of derivatives interactions were included. The other stuff was ... right? Namely, where the derivatives are distributed unevenly, so that the S matrix is ST, not just equal to, not just S to the power. So from the flat space point of view, it is clear that you can remove such terms by setting t equal to 0. Right?
Yes.
Looking at it in forward limit, but the way you got it is through CFT, the anomalous dimensions and so on, and writing down CFT sum rule. So from that point of view, why was it, why could you just erase those terms? Somehow they don't interfere, they don't talk to these terms.
Yeah, it's not obvious. Like it's actually something you have to check. So basically, the thing that you can check, like when you have those other kind of terms, like or terms that vanish in the exact forward limit. So in those the relationship between the CL coefficients and the lambda coupling constants. So this you can actually show that those other kind of terms, they're always suppressed by some powers of radius. It's basically something. It's not obvious. Like it's not that like it was something that was not. That's not true. Like I actually had to check that. That's a true statement, and actually that's a non-trivial check.
No, but for a given k, they will be subleading, but for a larger k, they would be leading, correct, compared to those terms.
No, it's basically since like if you have a fixed number of derivatives, you're like it's fixed like how which terms it can contribute. Like it cannot contribute to a large k term. It always contributes to like the number of derivatives actually dictate like what k it can contribute to. So
no, I was just wondering when can it be suppressed compared to because you were working with lambda k infinitely many terms, right? Let's say 100 terms.
Yeah.
Right now at 3 lambda 3 could have a t also, let's say, and then it would be subleading, but it is not subleading compared to a very large lambda. I mean lambda 30, right? So
yeah,
but your inequalities had all these lambdas playing with each other. So
yes.
Could they now start contributing?
No, because like if you remember, like the CL coefficients, they are basically coefficient of individual power of 1 over sigmas. So basically, it's not that one CL coefficient of let's say 1 over sigma, like the bound of that does not interfere with like CL coefficient of let's say 1 over sigma 30, things like that. So it's basically the bounds are basically for you can actually project to individual terms. So that's why there is a bound. So yeah, this is actually this is not a very trivial statement. Actually, the fact that you can project to different powers of 1 over sigma or different spins is actually that's why you actually have this kind of bounds at all. Otherwise, like you'll only have the chaos bound and that's it.
So, but in flat space, they are able to get these bounds involving other coefficients also, right? So, is there a way to get those from CFT? You on the bound, for the coefficients of s to the m, t to the n.
Since they have those other interactions, like from this setup, no. But like this is a very like specific setup with like this might not be the optimal setup to actually derive bounds. This is the setup where basically the possibility conditions and things like that are very obvious. So basically, I without even thinking much, you can actually derive a lot of things. But it's possible that when we know what kind of bounds we're looking for, we can actually design something which is like particularly suited for those kind of bounds.
Okay. So
like these are not optimal. So like and it's very likely that like those other kinds of bounds will also appear here as well. Like if you study some other setup.
Okay. Thanks.
Sorry, the second paper of Rastelli and company, the one that also looked at ADS, did they get bounds on the non-zero t coefficient terms that Abhijit was talking about?
I have to check. Their papers are kind of like marched together in my head. So like I don't want to comment, but like if I have to guess, I think in that paper no, but probably they are working on that. Either they have those bounds or they are working on those bounds.
Shuman and Shubham, do you remember? Do they get?
Sorry, can you repeat?
Well, Abhijit was asking the bounds that Sandipan is getting are only those that show up at t equals 0. Only for those coefficients that show up at t equals 0 in the S matrix.
Yeah.
Right, because all the derivatives are contracted on one set, so it's all S. But in the first Rastelli and company paper, the sharp boundaries paper, they got bounds on other coefficients as well. Now, the question was in the second paper where they try to start from CFT and re-derive their whole story. Are they able to bound only the t equals 0 coefficients or the others as well? We can move on.
I am at least not sure.
Yeah.
No, I clearly not remember.
Yeah. Okay. Thanks.
Okay.
Yeah, I think like my guess is no, I don't remember, but like yeah, if not, then they are like doing that like right now probably.
Okay.
Yeah, I don't want to go into the application. Like there are application for like RG flows with global symmetry breaking that like we know the effective action, so you can actually constrain the effective action, and you actually get new kind of bounds from these CFT arguments. But let me not go into that. Okay, let me now conclude. So let me now summarize the things that I really want you to take away from this talk. The first thing is like the most important point, that there are effective field theories that cannot be embedded in a UV complete theory. So this is basically a sharp departure from like the traditional understanding of Wilsonian effective field theory. And this is basically like something that we all know for like last 20 years or so. The second point is EFTs in ADS with or without dynamical gravity can be constrained directly from CFT axioms. And to me, this is actually a very clean way of deriving constraints because they follow directly from axioms that we completely understand. And more precisely, I actually showed that like from conformal bootstrap, you can derive precise constraint on high derivative interactions such as this. And a couple of other things that one can easily generalize this setup to do. For example, one can include loops and compute the same kind of CFT Regi correlators, and all the CFT theorem that I mentioned, it's valid even when there are loops. So we can actually just study effective field theories with loops. More interestingly, like the thing that I really want to study at some point is basically deriving similar bounds for external states with spin, such as like gravitons and things like that. It's also possible that stronger bounds can be derived from numerical bootstrap because like a lot is known in numerical bootstrap. Probably those tools can also be useful here. But a more general goal would be to derive some true general statements about asymmetrics directly from CFT axiom. That would be a really useful goal for this kind of program. There are many other things that can be done in this setup. And I truly believe like this is just the tip of the iceberg. And from this kind of argument, it's possible to derive a lot more, and it's possible to learn a lot more from this kind of setup. And actually, it's kind of amusing to me that even after so long time, like we can still say things about, like we still can find new things about like just simple scalar effective field theories. So stay tuned and thank you very much for the attention.
Thank you very much, Sandipan, for a wonderful talk, and I'm sure which was very tiring also. So thanks again for entertaining all the questions.